Morten til alle. Den halvtomme prop, er der nogen, der har aktion på den, eller skal vi have en mand i byen efter den? Jeg vil gerne have et svar nu.
Alle stationer, her er vagtchefen. Skyt er ankommet med provianten. Slut. Alle på prøvestanden. Der bliver bragt proviant ned til prøvestanden, så I behøver ikke at gå til hap for at spise.
In liquid fuel.
Men det kan være, det kommer
Jeg kan godt høre dig.
Hej til Ellen, hej til Ellen.
Ja.
Streamer
5.
Ja, okay. Jamen, velkommen her til det gamle BRV.
In English, yes.
Yeah, selvfølgelig.
Welcome.
Yeah. Well, welcome everybody here to the Copenhagen Suborbital Test Facility at the old shipyards, actually in the heart of the fair city of Copenhagen. We have a beautiful day here. It's a light westerly wind, about 6 knots, about 3 meters per second. It's 15 degrees, and as you can see, it's slightly overcast. It's beautiful. It would have been a nice day to fly, but this is a static test.
It is.
Yeah.
And we are, so the rocket is bolted onto the test pad, so it does not fly, unfortunately, or fortunately. The point is, of course, to measure the performance of the engine to see how it will perform, so it will be easier to model how the rocket will eventually fly once they go out to the Baltic to launch it.
Yeah, and this is a new rocket, a new type of rocket for the Copenhagen Suborbitals. It is a liquid fuel rocket. The earlier rockets that actually have flown, 4 of them, isn't it?
Yes.
4 of them have flown. That has been solid propellant.
Hybrid.
Yeah,
I
hybrid.
believe they've been hybrid all 4.
Yeah, hybrid. Yeah, with liquid oxygen and solid fuel, but now the fuel is alcohol and liquid oxygen as usual is mixed. And that is sort of that's the next stage. That's really a stage for a jump forward, isn't it?
Of course it is. Liquid fuel rockets are the professional choice, with a very few exceptions. I believe Virgin Galactic are using a hybrid motor in their spaceship too. But that is that's very unusual, especially for a manned space flight. Of course, the ultimate goal for Copenhagen Suborbitals is manned space flight. So they have chosen to switch now to bipropellant liquids, and I think it's a wise choice. When you look at the history of Copenhagen Suborbitals, I think the experience has generally been that hybrid rocket engines are good as long as they're fairly small. But the moment you scale them up to be 60-70 centimeters in diameter, you start to have oscillations. And as far as I remember, they've tried hard to combat these oscillations, but it just hasn't proven possible. So now it's.
But before we go any further, let us present ourselves.
Yes. I'm Steen Eiler Jorgensen. I'm president of the Danish Astronautical Society, and I have been following Copenhagen Suborbitals for many years now. I believe it's 6 years they've been working now. And you are?
Yes, my name is Jan Haugaard. I am a science producer for television. I have followed the founder of Copenhagen Suborbitals, Peter Madsen, since he was a crazy young kid building his own submarines and slowly graduated into hybrid rockets. I have covered via the radio and via television the growth of Copenhagen Suborbitals from a funny idea, a crazy idea here in the heart of Copenhagen, to this beautiful, fantastic volunteer organization it is now of lovers of the art of space engineering. This is a great day, I think. Like you said, we're graduating into liquid fuel. Actually, I believe in these days it's 101 years ago that Goddard flew the first liquid-propelled rocket back home in Texas, and after that we have the great Russian constructors Korolev and the mastermind of them all, Werner von Braun from Germany, who perfected the thing for its time as in his time as an Obersturmbannführer, actually in the SS. But they built nice rockets, and that led us to the mighty Saturn and the everlasting Soyuz rockets that are flying today. But now there's a new a new one added to the family, a new prototype, a new hand-built piece.
Yes, and it's actually interesting to see how little rocket science has progressed over the past decades. Peter Madsen is very open about this rocket being inspired almost directly from the V2 rocket of Werner von Braun's from World War II, and the propellant is I believe is more or less taken directly from the V2. I believe the V2 flew on alcohol and hydrogen peroxide. Hydrogen peroxide is not used as an oxidizer in this test, it's liquid oxygen. But I believe the point is later on, once they develop this rocket into a turbine pump-fed rocket, that the pumps will be powered by alcohol and hydrogen peroxide. And so there are still some design elements from the V2 that you can see in the HEAT-2X rocket.
Yeah, well, basically you can see for all rocket, the important thing is to keep the combustion running once you get above sort of 30,000 feet, 10,000, 12, 15,000 meters. There's no more oxygen, so you actually have to bring your own oxygen. That's basically why you have to burn the fuel, whatever it might be, and today it will be alcohol. To burn it, you need oxygen. So you bring it along in sort of compressed form.
Precisely.
Yeah. And today, basically, the thing is to release that oxygen and the fuel. They are both in pressurized tanks, and to release it in a steady flow without any kind of vibration, bubbles, anything like that. That's the big art of this thing of flying, isn't it?
Yes, it is, of course, to maintain a steady flow. That is also why they have chosen to study the use of turbine pumps. Now, the rocket that's going to be tested today does not have pumps on it. It's purely pressure fed, and as far as I understand, both tanks will be pressurized to a pressure of 20 bars. And
that's 10 times the pressure of a car tire, for example.
Yeah.
Yeah.
And it will be and the propellant and the oxidizer will then be moved into the by pressure, pushed into the what's it called, the injector that mixes it, and it will be ignited inside the combustion chamber and blown out of the nozzle.
For those who know about cars, it's the injector is kind of the carburetor. You mix the gas and the air, the oxygen, and then it continues into the nozzle, which is like a trumpet or something like that. You know. And when we're talking about turbo pumps, is as when the rocket gets to a certain size, you can't pressurize. I mean, it's like if you buy a bottle of gas, propane. That's what you call it in English. For your cooker at home. or for your camping, for your camper. It's like that basically. You have oxygen in one bottle, and you have alcohol in the other, and the pressure will blow it out. If you ever try to sort of knock off the valve of a propane bottle, you'll see it comes out with a big whoosh.
Precisely.
Yeah. But when it becomes bigger, it has to be even stronger than what you compress it for. So you use pumps.
Yes.
That's why you're talking about turbine pumps.
Yeah. Also to keep the pressure steady, because of course when you have a pressure-fed rocket engine, the exhaust velocity will be very high in the beginning, where the pressure is high. But as more fuel is being ejected from the tank, the pressure will drop, and thus the mass flow will decrease. So the thrust curve, the thrust of this rocket engine as a function of time, will decrease exponentially during the burn. And that is of course also something that you will combat by using turbine pumps. That way you can keep the mass flow steady all the way through the burn.
Yeah, and it's a question of a steady flow all the time, a steady flow. As soon as you get vibrations, bubbles, and so on, that is especially what you have to look out for in these experiments. The steadier, the better, and it has to burn completely steady for. Today we're aiming for 90 seconds, 1.5 minutes.
90-second burn, yeah.
Yeah.
That's a long burn. That's the longest burn Copenhagen Suborbitals has ever done. I think the longest they've done so far has been a little less than a minute. So now they're aiming for 1.5 minutes. And of course the rocket is more or less configured to fly right now. It doesn't have a payload on top, and of course it's not in a state to fly, but it's mounted as a rocket on top of this test stand, and if this rocket were to be launched with this engine, it could in principle propel the payload to an altitude of over 100 kilometers.
Yeah. Yeah, and this is the first rocket where of the series that actually is able to reach the stated goal of Copenhagen Suborbitals. That is sort of to make a suborbital flight
into space.
Into space, like Alan Shepard, like the first American flight.
Precisely.
That was in 1961. That is the stated goal, the mission, or whatever we call it, for Copenhagen Suborbitals. And we have to stress here that this, of all of the rocket projects in the world, of all of the space projects in the world, this is not a cash cow operation. We're not trying to bleed government or big companies or people with rich people for lots of money. This is all done by volunteers, and it's supported by clever and far-sighted private companies, high-tech Danish companies, and it is supported by the Association of Danish Engineers. What do you call it? Civil engineers? No, civil engineers. If the Danish periodical, the periodical of the Danish Association of the Engineers, called The Engineer.
The Engineer.
It is seen from the outside is a very, very beautiful movement, you can almost call it, of people, of engineers that see in this. You can almost say that the artists finally have found their way back into the art of engineering. This is certainly a piece of art. If you look at it that way, then it is truly a fantastic installation. And we have to stress it's actually within the city limits, of the inner city limits of the fair city of Copenhagen. Right next to the Art Academy and the Royal Palace.
In fact, we're only a few meters away from where the Eurovision Song Contest was held just 3 weeks ago.
Yeah. So there's a huge. This used to be a very big, major shipbuilding site, one of the old ones, or one of the old rust industries of Denmark, and there are some of the big assembly buildings, enormous assembly buildings for ships left here, which is also one of the reasons why Copenhagen Suborbital is situated here, is because there is a multitude of very practical and useful buildings that are not too they're a bit outdated, so they're not too precious. You can do more or less what you want, and also that probably has to be stated. The owners of this property, they actually they bear with this beautiful piece of civil engineering, art of engineering. It actually is. We have to remember there's something called the art of engineering.
Certainly.
Yeah, and this is it. And that is my, I don't know, we can ask, you're an engineer yourself, that is this one reason why engineering is a very sober trade, and here is something that is,
Can be.
yeah, I mean, that's how I read about it. It's sober in many ways, it's fantastic in other ways too, and here you have something that is fantastic, bordering on the limits of art, in my opinion.
This is a unique project. I don't really know of other projects in the world which is truly, grassroots spaceflight. Spaceflight is usually either done by amateurs, in which case it's on a very small scale, or if it's on large scale, and manned spaceflight is always done on a professional level, where you have companies that have investors, and investors obviously need to have some return on their investment. So they need to have deadlines, they need to have clear goals, they need to know exactly when these goals will be reached in order for their investment to have some sort of return. And this is quite the contrary. This is people doing something in their spare time for fun, with the goal of launching humans into space. So it is really grassroots spaceflight.
Yeah, it's truly. We can see here, I don't know which of the feeds. We have 4 feeds going out now. One from the... Yes, that is a feed from the southern side. Actually, in the shadow lies the big flame grave, or the flame ramp that will feed the flames out towards the side, so it doesn't burn away the concrete below or blast away the concrete below the rocket. There's a ramp there that will be flooded with water and give us some impressive, very impressive clouds of steam. Actually, it's water vapor, isn't it?
Yes. The water is being ejected to dampen the sound and vibrations during the burn. And of course, when you have this flame with high temperatures being ejected at such high speed, it will evaporate completely a lot of the water that comes out there. We have some pictures of the test stand that we'll try to show you shortly, so that we can see what it looks like. Yes, here's a picture showing a test where the water is being the water sound suppression system, as it's called, is being tested, and you can see huge amounts of water being ejected in very short time. Of course, this in this burn, the engine is supposed to burn for 90 seconds, so there needs to be water enough.
Yeah, at least a cubic meter per second, something like that. Yeah, I suppose so.
Impressive. Yeah.
Yeah, that's a lot of water. But luckily, it's right next to a dry dock that has been left full of water, so there's plenty of water to pump.
We have enough water.
Yeah, there's enough water. Yeah, right. We have to, maybe we just do a little recap here. We are now standing by for the test run. Yeah, Now we're standing by for a test run of the new rocket engine HEAT-2X of the Copenhagen Suborbitals. In a little while we'll have Jonas. Jonas, one of the Copenhagen Suborbital experts, talking about what?
Nerd talk.
Yeah,
we're going to have a nerd talk.
Yeah, we're gonna have one of the guys with I suppose maybe with the dirty fingernails, one of the guys, one of the super experts coming to visit the studio in some minutes. What we can see now, we still have the signal going out. Is still the camera shooting towards the south. You can see from the shadow where we are now 30 past midday, 0:30 p.m. You can see from the shadow where the southern direction. The buildings in the background, the tall smokestacks and so on. That is one of the power plants of Copenhagen. And that's what you can see there. Also in the foreground, there's all of the cameras. There's actually a manned camera. I think that might. No, that's not the one we were looking at. But there's a manned camera right to this side, and he's in case sitting in an armored position, built out of iron. A thick iron plate. He's protected. He's one of the veterans of the Copenhagen Suborbitals. But we are standing by now, waiting for Jonas. He'll come and give an interview in just a few minutes. But we wait for him. Right now, people are starting to come by. It's still a couple of hours before ignition time. But people are making a day out of it. It's a very nice part of Copenhagen, this place. It's sort of both land and sea. It's an old landfill, this place. Actually, right here where we're sitting right now was right in the middle of the Battle of Copenhagen in 1807 between the Danish King Frederik the Sixth and Lord Nelson of the Royal Navy of Great Britain. That was right here where we're sitting right now. It was a huge sea battle. Yep.
Yes. Jonas Bjarnø, welcome to to our recreational vehicle here.
Thank you.
With lots of electronics inside of it. I want to ask you what's your role on this project?
Well, for now I'm on board as a technical advisor primarily, and I'll be helping out with the payload for HEAT-2X once we've completed this test successfully, hopefully, and I'll also be doing some measurements today on input to the guidance system, magnetometry and accelerometer data coming out of it.
So you're a guidance system guy.
Yeah, I'm a bit all over the place. So guidance,
okay.
Thermal, trajectory, analysis, thermal analysis, fluid dynamics, and so forth.
And the test today is a little special because this is not just a test of the rocket engine as such; it's also a test of the guidance system. Of course, the rocket is strapped to the pad; it's not going to leave. Hopefully, it's not going to leave. Hopefully, it's going to stay in place. But the jet vanes are mounted, right?
Yes, or two vanes.
Two vanes.
Yeah. And in essence, this is what is normally referred to as a full-up test. So you're taking a little larger risk than just testing the engines. You're actually trying to test the full vehicle with the flight version of the tanks and the plumbing systems and all the control electronics and the jet vanes also in this case. So the idea is that by actuating the vanes during the test, we can generate a set of data that tells us how much vector control power do we have at certain stages throughout the burn.
How do you measure that? Do you have some strain gauges on the
Exactly.
vanes?
Yeah, we have two vanes. One is statically mounted in the flow, and that has a single-axis load cell on it. And then from that we can derive the drag coefficient on just one static vane. And then we have another vane which is actuated, moving plus minus 20 degrees. And on that we also measure the drag force versus inclination on the vane itself. And that then gives us control, the control force or control torque versus angle at a certain point throughout the burn.
So you have a jet vane inside the rocket engine exhaust that is moving plus minus 20 degrees.
Yes.
That sounds like a lot.
That is a lot. Normally you would say that the vane geometry that we've chosen for this test actually stalls at around 12 degrees. Moving beyond that, the flow behind you becomes very turbulent, so you're generating a lot of drag, and it actually requires quite a lot of power to move it to 20 degrees. But this is it's a static test, so there's really no reason not to try and go to the furthest position we can, and then see, well, how much control torque can we actually generate. And the penalty for doing that is, of course, that once you're moving your vane in the flow, your oncoming area increases. And that means that the thermal performance of the vane actually becomes an issue, because you're putting more and more energy into the vane, and of course at some point you're going to reach a level where the copper vane has reached the temperature that makes it melt, exceeds its melting point. That's the penalty you get. But essentially, if for this test, if we are able to get 20 or 40 seconds of continuous data, you don't really have a problem, because then you can extrapolate for the remainder of the burn.
Is there any sort of cooling inside these vanes?
No, these are static from that perspective. So you're working off the total heat capacity of that block of copper, and the static vane is simply steel. And of course that means that at some point you might reach a situation where you saturate, and the vane then starts to melt or sublimate.
The last rocket that was tested statically was the Sapphire, right?
I believe so.
With 4 copper vanes, and they did not show any noticeable erosion after the test.
No.
Is that right?
Yeah, I think so.
So how much do you think there will be any erosion here?
Well, you need to keep in mind that the Sapphire test was only an 18-second burn. That's fairly short duration, so probably the vanes never reached an equilibrium temperature. For this test, you're going to be running it up to 90 seconds, meaning that you will certainly reach an equilibrium temperature at some point. The question then is, will that equilibrium be higher than the melting point of the metal? For the copper vanes, copper has a very high thermal conductivity, so the entire block of copper will be more or less isothermal, whereas the static vane, which is steel, has a fairly low thermal conductivity. So I would expect to see that the leading edge of that vane will be degraded somewhat at the end of this test. It might fail altogether. In itself, that's not really a big issue if it does fail, because it'll give us the drag for the beginning part of the burn, and beyond that, it also allows us to look at some other effects. There are, for instance, an effect called shock interference, where you have two veins situated across from each other, and the shock wave from the flow hitting the top side or the leading edge of the vein might actually intersect each other. And that could give you some localized heating that's very hard to model. So you would also want to test to see if that sort of phenomenon occurs.
Of course. We might have a picture of the jet vanes actually that we can look at.
Okay.
We're working on that. In the meantime, can you tell me, are you measuring the temperature of the jet vanes?
Yes.
During the burn?
Yes, and it's actually the combination of measuring temperature and force as the burn progresses allows you also to validate. We have a thermal model of the vanes for a statically mounted vane. So this allows us to sort of verify that model being correct, and in the future that means that we could be much better to predict how this type of vane structure will perform. So we put a lot of emphasis on getting both the temperature and the drag data at the same point in time.
We can see a great picture of the vanes now. So there are only two vanes inside the exhaust on this test. And the copper one to the left is the one that you're going to move, plus minus 20 degrees, and the steel one is static.
Yes.
Okay. You can't see it from this image. How big are these vanes?
They're around 20 centimeters on the base, and the tip end is, I believe, 14 centimeters, I think. Okay. Mass-wise, it's around 5 kilograms per piece.
5 kilograms each.
Yeah.
And here we have a picture of the business end of the Sapphire rocket, the first actively guided rocket that actually flew very nice last summer.
And you will note that the vanes there, they are quite a different shape. The vanes for this test, they are built to allow for a bit more aggressive maneuvering, because you need to input a larger force to control a rocket this size. Remember, this rocket has a very long length to diameter ratio, so it will have a tendency to, if disturbed during flight, it'll take quite a long time to settle into to its correct orientation if you only rely on the fins. So in essence, you want to be able to put in a lot of control force quite rapidly to stabilize it. If for instance you encounter shear winds or something like that. So to do that, the vane area is fairly large, and the vanes themselves are fairly slender, which means that a smaller angle movement will produce a larger control force. Also, you can see the backside of the Sapphire vanes. They're quite blunt, and that's not really efficient in terms of drag produced by the vanes. Remember, the vanes are situated in the exhaust flow, and the exhaust flow is hypersonic, so you have exhaust coming out at 3.5 kilometers per second, and if that flow can't really, once it's passes beyond the vane, it'll take quite some distance to collapse in behind itself. And that means you're getting sort of a turbulent wake behind the individual vanes, which costs you actually quite a lot of thrust. And by doing the other geometry, you can see it sort of tapers to the backside quite. It's somewhat more elongated, meaning that void that's created behind the vane will be filled by material.
It's basically just a more aerodynamic shape.
Exactly. So that sort of gives you a better drag profile. At least that's what we're hoping.
These vanes, they're then controlled by a servo motor.
Yes.
How fast are the vanes able to move? I have this idea that they need to move extremely fast.
Yes, and they can. Fleming can give you the correct number, but it's tens of milliseconds to go from side to side. And
a few tens of milliseconds
yes,
to go from one out point to the other.
Yeah.
Okay, that's fast.
Yeah, perhaps 100 milliseconds or so. I don't remember the exact number, but it's on that scale. And yes, you want to be able to do that because, of course, the faster you're able to do that control, the higher rates of movement your rocket can tolerate, and you can still recover. If you were moving the vane fairly slowly or not able to move it quickly, that would mean that if the rocket starts to spin at a rate, that maximum allowable rate would be much lower.
So basically, what you hope to get today out of this test is measurements of how these vanes perform, and you will then use these results as input for your control software.
Exactly.
And this rocket is supposed to fly live this summer?
That's what people are hoping to do.
That's the current plan? Yeah. Do you know when?
I would suspect late summer, late August, beginning September would be provided this test is successful and we get all the data we need. That would be a realistic time frame, but it depends on a lot of other factors as well.
Of course.
Weather being one of them. This rocket requires, due to its larger size, it requires more amenable weather conditions.
Yes, of course. Yes. Is there anything you want to add? What are you? Is there anything you're nervous about today?
Well, from my perspective, there are a lot of things you're testing here, and of course, a full-up test always has a lot of risks involved. Normally, what you want to do is sort of incremental testing, but essentially, this allows us to evaluate a lot of parameters we wouldn't otherwise see. And for instance, here we have the rocket fully loaded with liquid oxygen, and we have that for about an hour before ignition. That means we can also use this opportunity to check all temperatures throughout the vehicle, and we will then be able to predict what temperature will the electronic section be at, and the motor section, and the parachute section, and we'll be measuring temperatures all over the place, right? And the idea is, of course, that knowing this now allows us to improve the electronics or move it around if it turns out we have a thermal problem. And that's actually something that's fairly difficult to test without putting the entire vehicle together and loading it with liquid oxygen. So in that sense, this also provides us with an opportunity to get some data that would otherwise not be available until you actually have the rocket on the pad. And then, of course, it's a little too late to do much about it.
For those of you just joining us, I'm Sten Eiler Jørgensen, and I'm sitting here with Jonas Bjarnø, who is involved in the guidance system. We've talked about jet vanes, we've talked about servo engines, we've talked about deflection rates, and do you know, you've been out on the pad
Yes.
earlier today. Do you know when what's the status out there right now?
Well, the status is they've completed the loading of the liquid alcohol, and we are now awaiting start of liquid oxygen loading. And there are some processes that goes before that, so I would expect that to occur within the hour. And of course, that takes quite a while because we're loading a fair amount of oxygen this time.
How much oxygen and how much alcohol is going to be in the rocket?
I believe we're ending up with a total amount of about 1,200 kilos in all.
1,200 kilograms of fuel and oxidizer combined.
Yeah.
So is that 600 kilograms of each?
They're volumetrically identical, so you have the same volume, but of course the density is not quite equal. So you will have a little bit more alcohol than LOX to get to that point.
And the oxygen tank is on top?
Yes.
And the alcohol tank is below?
Yes.
And the oxygen is being let down through the alcohol tank?
Yes.
In a pipe in the center of the alcohol tank?
Yes.
And there is a cooling spiral inside the oxygen tank?
Yeah, a heat exchanger simply to keep it cold as we go along. Aerodynamically, that's your favorite solution, where you actually pipe the liquid oxygen through the alcohol tank and through the engine. But it has its own difficulties because you're actually cooling the alcohol quite a bit by doing so, and you don't want
heating the oxygen.
And heating the oxygen, of course. So that's not an optimum condition for that perspective, but it saves you from having pipes going down the side of the rocket, which is an aerodynamic penalty when you actually fly it.
And we actually have a picture here of the HEAT-2X rocket. The rocket as it's going to look for launch next summer, and below that we have a cut-through view where we can see the oxygen tank on top of the rocket to the left, with the heat exchanger inside of it to keep the oxygen cool, and below that we have the alcohol tank and then the engine. So the oxygen and the alcohol are going to be mixed more or less 1-to-1.
Yes, by volume. So the same volume of the two components are mixed together, and that gives you a little bit different flow rate in kilograms, but you aim at getting the same volume of the two components.
And these tanks are pressurized to what, 20 bars each?
Yes, the alcohol tank at 22 bars, and I believe the oxygen tank at 18 or something like that. Yeah. So the configuration shown there is essentially the one we have sitting on the pad right now, right up to the parachute barrel at the very end. The payload on the top will be changed from the view you have there to the flight version. We'll be flying a smaller, we call it a re-entry demonstrator payload this summer, which is essentially just a tiny capsule with aerodynamic properties that allows it to re-enter statically. And from that we then put out a small balloon to test that part of the system.
And a balloon is something that's halfway between a balloon and a parachute.
Exactly, and these are notoriously known to be difficult to test on ground because they're built for hypersonic conditions. But hypersonic at very high altitude, so conditions where you have a very low density of air, but moving at a very large speed. And we would like to take this opportunity to actually try that design out before you put on a bigger capsule. And we just last week here we had a test in a wind tunnel using a small balloon design, which is a prototype for the ones that's going to be flying with the RED.
But when you look at the rocket on the test stand right now, there's no payload on top, right?
No, it's simply terminated right at the parachute section. You can see sort of a barrel shape at the very end.
Yeah.
And we've loaded that with an old spare parachute to get the right thermal mass.
Oh.
And then we'll be measuring the electronics on the underside, the temperature on the underside of that barrel, because that's where the flight electronics will eventually sit. And as you can see from the design, that unfortunately that section is right on top of the oxygen tank, and the liquid oxygen tank will get to a minus 180 degrees or so, and that doesn't really go well with standard electronics. So we have had to get a little creative on the top with some MLI insulator blankets and so forth to simply generate a thermal gradient that allows us to put electronics in there.
So you're worried about the electronics on top of the oxygen tank getting too cold?
Yes, exactly, because we will be carrying quite a lot of batteries there. And of course, your standard nickel metal hydride batteries don't take too well to a minus 50 degrees C. So we hope to keep them a little bit warmer, and that's most easily done by passive means. So all that is installed for this test, and we'll be looking at the temperatures right when the LOX has loaded and when the vehicle has sort of reached an equilibrium state where all temperatures are stable before the test. And we'll be looking at what temperatures will be experienced at different points in the vehicle.
I know that everybody is curious about when this is going to happen. Originally, the message was that they would aim for a test firing of this rocket engine at 1400 Danish time, which is 12 UTC. And what's the last word?
Well, I haven't heard anything else, but my expectation would be that once the LOX loading starts, and that procedure itself will probably take half an hour to an hour, and after that there's a soak time of perhaps 3/4 of an hour. So optimistically I would say not before 3 o'clock.
Not before 3 o'clock.
No.
So as you can hear, guidance specialist Jonas Bjarnø now telling us that we'll probably not see the test fire commence until 3 Danish time, which is 1300 hours UTC. And of course that is because the liquid oxygen has not begun to be loaded yet. Do you know when they will start loading the oxygen?
I don't know at this time. No.
No, okay. Well, Jonas Bjarne, thank you very, very much. This was very interesting. We certainly hope that you will get some data for your guidance system,
yes.
so that we'll have as beautiful a flight of the HEAT-2X rocket as we had with the Sapphire rocket last summer, which was extraordinarily straight.
That was nice.
Yes, that was very nice. Thank you very much, Jonas.
Okay, thank you.
Once again, for those of you just joining us, my name is Sten Ejle Jørgensen, and I am inside our recreational vehicle with Peter Mærsk Møller, who is doing the mixing and streaming, and we're looking right now at the VTC3 test stand, the vertical test cell 3, number 3 because there have been 2 others, and this is so far the largest one that has ever been built. And as you can see now, the HEAT-2X rocket is on top of the VTC3 test stand. There's no payload on top of it, but it's loaded currently with liquid alcohol, and will hopefully shortly be loaded with liquid oxygen. And we are currently looking at a expected time of firing of around 1300 hours UTC. And with those words, I think we'll be taking a short break and talk to you in a few minutes again.
Sådan der, ja, ikke? Yes, well, my name is Jan Hauger. I'm back. We are watching a live stream from the test center of the Copenhagen Suborbitals setup test of their new rocket engine, the HEAT-2X. We have our main shot here is we see the test stand. It's a static test. I have to remind you, it's a static test. You can see the rocket stack in the middle of it. There's a huge concrete envelope around it for protection. It's all built in an old shipyard. You can see to the right of the picture. You see some of the huge assembly halls of the ancient shipyard that used to be there. It's all within the city limits of Copenhagen. Actually, we're looking towards the center of Copenhagen. You can see some of the skyline of Copenhagen on this picture in the background. Well, we have actually right behind the rocket stack, we have the Royal Palace of Copenhagen, and we have the big, for people who have visited Copenhagen on some of the big cruise ships right behind, right in the background here, we have the port of Copenhagen with the cruise terminal behind us. So we can say it is a completely unique setting that we're watching here. Actually, a rocket test, a live test of a static test, be it in the center of a big city. It is the new. We're going to watch. It will be about 1500 hours Danish time. That is GMT +2. We will see the new rocket engine being tested. It will momentarily, for 90 seconds, develop an effect of about 100,000 horsepower. It is the mission and the goal of the Copenhagen Suborbitals is to launch a spacecraft into suborbital space at some undisclosed future date. But I can tell you so much that the launch pad for the actual next test launch of this HEAT-2 rocket, the launch pad is being prepared. It is being built right now and assembled. It is a floating launch pad, like the style of sea launch, and it will launched. It will actually, the rocket will be, after, if successful today, the rocket will be taken to the east of the island of Bornholm in the Baltic. That is in a secluded area, military area that can be sealed off for any traffic, so that the next test launch will happen sometime midsummer in a couple of months in the Baltic. And preparations are going ahead for that as we speak. There's a huge optimism around this. It's a major step for the Copenhagen Suborbitals, the volunteer organization of young, mostly engineers, but also other technically interested people who here find a truly visionary, almost artistic project to throw all of their excess energies and talents at. It is a completely non-profit, open source project, in stark contrast to all other space projects in the world. This is not the driving force. Is a dream of space. It is the dream of actually playing with heavy equipment, and it is also somehow, it is almost a dream of society, because Copenhagen Suborbitals is not only technically minded people, engineers, but it's also actually supported by some of the finest companies of Denmark, including the Therma radar and space remote sensing company, the Weibel tracking radar systems. We're talking here illustrious name in the Trane satellite phone. That is some of the finest high-tech companies of Denmark that actually supporting this, especially supporting the launch technicalities, which can't be done without sophisticated tracking and remote sensing systems. Right now we expect that you'll have this tiny white cigar. You'll have it actually developing for 90 seconds, 100 horsepower, 100,000 horsepower for this, showing the miracle, the incredible creation of the rocket engine. Actually, these days, I believe it is more or less exactly, it is 101 years ago, in 1920, no, it's 91 years ago, I'm sorry. Or 99 years ago. 99 years ago that Goddard, the famous American inventor and researcher, fired the first liquid-propelled rocket. Later on, the technology was adapted, if not to say stolen, by the SS and developed by famous for the German rocket troops by famous Werner von Braun, who later went on to lead the American. After the war, he was captured and bought to lead the American space project. Parallel to that, you have the incredible genius of the Russian space program, Sergei Korolyov, who himself, who on the basis still of some of the V2 rockets, some of Werner von Braun and the SS rockets from Germany, developed the Soyuz rocket, which flies to this day, the most fantastic space elevator ever built, with up towards 2,000 launches and very, very few failures. That right now it is the elevator to the International Space Station, for example, with regular flights, monthly flights going up there, and it's that's the way it's been for quite a long time, since the retirement of the space shuttle a couple of years ago. That might all change now with the Dragon 2 from SpaceX. We've seen it. It's been tested just in orbit. That is supposed to, but that's supposed to be a shuttle going back and forth from the space station, carrying up to 7 astronauts. I suppose then you can sort of increase the crew of the International Space Stations to 5 persons, as opposed to now, I don't know, they're down to some kind of skeleton crew of 2 persons, or anyway, not more than 3 cosmonauts at the International Space Station, due to sort of lack of transportation, because all we got right now is Soyuz rockets and Soyuz spacecraft to take us there. Time counting down. It's 13:10. It'll be an hour and 50 minutes to the firing of the HEAT-2 rocket engine of the Copenhagen Suborbitals. It is a
system. Maybe they can figure it out anyway. But I think that the main thing today is to have the engine ignite and burn for 90 seconds. And of course, that's, as Peter Madsen has stressed so many times before, the charm, the beauty of a liquid-fueled rocket engine is that you fire it, and once it's burned out, if you haven't destroyed the engine, you can just fill it up anew and run it again. And do it again and again. So I believe that if this is a non-destructive test, this is the same engine that will be used next summer.
Yeah. but as you say, like Jonas, and then like Jonas has been explaining, and that is also the remarkable thing of the Copenhagen Suborbitals society here, is that you actually have people within this little organization studying like really seriously high-tech, complicated questions such as digital gyro and the feedback of gimbal rockets or gimbal vanes in the exhaust, etc., etc. And actually these things are, if not being developed, then sort of Copenhagen Suborbital actually manufacture, design and manufacture their own versions of everything.
Exactly. Yeah. Everything is home built and home welded, and I think the only thing that's being bought off the shelf is electronic components. Yeah. Things are being soldered together in the electronics department. They have a special variation of the Arduino called the CS-Duino, for Copenhagen Suborbitals Duino. So there are a lot of things built around off-the-shelf components, but being put together in a way that has never been done before.
Yeah, and also it sort of accumulates, and also I can say that people, the crowds are showing up now. People are making it a day out. This is a fantastic picnic on the concrete plains of the Copenhagen Suborbital test range here, actually within the city limits of Copenhagen. The people are here with their kids, and they're buying hot dogs and and making a day out of it. It's a beautiful day. I don't know, the wind is picking up a bit maybe.
It's a little windy, but mostly sunny.
Mostly sunny. It's a beautiful day, you must say.
It certainly is. It's a great day for test firing a rocket engine.
Yeah, exactly. To have a picnic, go and watch test firing of a rocket. It might be a bit boring, so wait, but it sure will be worth it, because you won't hear or see anything like it at all until the next time here. And there's nowhere in Scandinavia, and not even in Europe, where you can actually Max, han må være lige herude.
We've just found out that the text at the bottom of the screen right now says that we are looking at a firing time of 11 a.m. CEST, which is obviously wrong, because that's almost 2 hours ago. It's supposed to say that we are looking at a time now of 1300 hours UTC, which is 1500 hours Danish time, since Denmark is 1 hour ahead of UTC, and now we also have daylight savings time, so right now Danish time is 2 hours advance of UTC.
Yeah, so maybe we just should We are waiting to see the test burn of the new rocket engine HEAT-2 of the HEAT-2X of the Copenhagen Suborbitals. We are at the test facility at Copenhagen, actually. In the fair city of Copenhagen, not far away from the Royal Palace and the Art Academy and the Opera House. My name is Jan Haugaard, and
my name is Sten Eiler Jørgensen.
Yeah, we'll be with you, the rest of this fair and sunny afternoon. The wind has
providing commentary as best we can to tell you what's going on. Hopefully we'll also have a few more interviews with people from the project. We had earlier on Jonas Bjarnø, who told us about the guidance system and what they hope to achieve in today's test, and later on we're going to have some other guys in here. We're inside a recreational vehicle rebuilt for this production. We have a lot of screens and wires, and maybe I should take a picture and tweet. Oh, we also have we have a hashtag on Twitter. You can tweet us using the hashtag HEAT-2X. That's HEAT-2X. And I can see that we've already had some tweets here, and you can ask us questions. Emil Vind says Danish time is GMT +1. That's true, and we also have daylight savings now, so it's GMT +2 right now. We also had we've had some requests from solarracing.org and from Ben Brokert, who asks us to announce who's talking and how long it is until the HEAT-2X test every 15 minutes. So that's probably a good idea.
Yeah, well, we can give it to you right now. It's about 1 hour and 35 minutes. The stipulated time of the firing of the HEAT-2X.
And as Jonas told us, what we're waiting for right now is the beginning of the loading of the liquid oxygen. Once the loading of the liquid oxygen begins, it will probably be in the vicinity of an hour until firing. And as far as I can see, the loading of liquid oxygen has not yet begun. Of course, once the loading of liquid oxygen begins, we will be able to see liquid oxygen boiling off somewhere. We'll be able to see
there will be a bit of
steam,
vapors coming around. Yeah, there's no doubt about that. So it has not started yet. So if we are going for a deadline of 1500 Danish, then the fueling of the liquid oxygen should happen within the next 15 minutes. Usually, I don't know, it takes about 20 minutes to tank to fuel the liquid oxygen, I believe. I don't know, something like that.
I don't know actually. That may be. And then of course, once the liquid oxygen is loaded, once they close the tank, they start the pressurizing.
Yeah.
And as Jonas told us, the liquid oxygen tank is going to pressurize to somewhere around 20 bars.
Yeah.
If we sound a little confused and or happy right now, it's because both of us have just been handed a very nice piece of Raspberry Pi, which is extremely appropriate since everything inside this vehicle is running on Raspberry Pi. I've just been told that we have a cupboard full of Raspberry Pis right behind us. And I think I'll try to take a picture of that and tweet it later on. But now we also have a real Raspberry Pi in front of us with real raspberries. That looks very good.
Yeah, well, the weather is with us, and I think there's going to be a record crowd around here. Anyway, yeah, there's a lot of people here, and people actually support Copenhagen Suborbitals by paying a nice $30 ticket to come and watch this. It's a very, very nice thing about this thing is that people actually support this. this society of rocket enthusiasts, of people who are actually, this is really done during their spare time. Well, the founder of Copenhagen Suborbitals, Peter Madsen, I don't know, he's a fanatic, so he doesn't really count, but I suppose he's the only one who's on it full time, and for him it's like 24/7. You know,
it's his job,
yeah,
basically.
Yeah, that's always been. He's always Peter's career is interesting. He started out playing with his own submarines, mini submarines, which became bigger and bigger. And then he graduated into rockets, and created the first rockets of the Copenhagen Suborbitals, which were hybrid rockets with solid fuel and liquid oxygen. And now today is the great graduation into the realm of the great forefathers of Goddard and von Braun and Karaljov, the great rocket builders of modern times, the ones when the first Sputnik went up, lifted by a rocket, by a Soyuz rocket. Allen Ginsberg, famous American poet, heard about it in Paris and wrote in a letter home to his father, "This is the greatest thing since fire." Yeah, we're in and that's what it is. This is this kind of vehicle is something that our forefathers didn't know about, couldn't even dream about it. My own father, he hardly even, he didn't really ever get it. Anyone over 70 couldn't really understand it. This is more as revolutionizing. It's part of the huge steps forward of mankind, like airplane flying and the great medicine, the radios and the great medicinal discoveries. And the rocket gave us the view of Earth, of the globe, of planet Earth, and it gave us the right to dream about the stars. Just like one of the mottos of Copenhagen Suborbitals, it is Ad Astra, we're going to the stars. And I'm here with you, with my colleague Steen. We are trying with keeping the audio open for the live stream from the testing of the new rocket engine of the Copenhagen Suborbital Society, and we're keeping the audio line open for you, telling you about the test burn that will occur in 1.5 hours at 1500 Danish time, which should be 1300 UTC, Universal or Greenwich time. We are waiting for the tanking of the fueling of the liquid oxygen, which should occur pretty soon. You will notice it. You are now on the camera looking towards the west, and you should be able to see when the sure sign that the liquid oxygen fueling has started is that you will have some of the oxygen which is pressurized, and that is therefore frozen, will boil off, and you see small wisps of vapor around the bottom of the rocket, around the booster. We can see what is happening here. I don't know, maybe my glasses are dirty. I'm not sure, I can't see it. Maybe they're getting ready. It's hard to tell right now, but it should be sometime soon. The people are arriving. I think there must be some hundreds out there right now. They're making a picnic out of it. It's one of the great things. It's one of the great attractions of Copenhagen. This strange, wonderful part of Copenhagen. This is actually part of the ancient defenses, sea defenses of Copenhagen. It were among the more romantic neighbors of this test facility is the famous squatter town of Christiania, and right to the west in the background, you can see on the picture, you have the center of Copenhagen with the Royal Palace, with the Opera, with the Art Academy, and the harbor of Copenhagen, the big terminal of the cruise ships that are coming in on a daily basis. The harbor is full of these enormous vessels, and I believe that it has been announced aboard, at least the audio, the experience of the audio of this event is something in itself. It is a fantastic noise for anyone who loves crazy engines. This is a place to be this afternoon. People are actually paying a ticket to get in here. They actually of $30, 150 Danish kroners that way, showing their willingness to support the Copenhagen Suborbitals, the wonderful this wonderful society of young engineers and technical enthusiasts who man this up and who fill all of the functions of a big spacefaring organizations right now. As one crew is preparing the launch, the test firing of the HEAT-2X, another is completing some of the pontons for the floating launch pad of the HEAT-X, which will be used if, providing everything goes right with these tests. There will be an actual launch this summer from the floating launch pad in the Baltic, in a test area that actually has been sealed off, that Copenhagen Suborbitals will loan from the Danish Navy, who have been not only have been very, very sympathetic by actually getting the certifications and the permits, etc., but also are patrolling the whole area on the day of the days of the test launch. It's actually turned into quite an event, in a yearly event. This launch campaign is now, next time it will be the 5th time, I believe. Yes, it's the 5th summer, consecutive summer, where Copenhagen Suborbital have its launch campaign on the beautiful island of Bornholm in the Baltic, and east of the island is a military naval area that can be blocked off for any traffic, so the test can be conducted safely, which has now happened 4 times. And if everything goes right today, probably will happen a 5th time next year. And thanks, actually, there's 2 sides of this Copenhagen Suborbitals. There is this well-manned and quite numerous volunteer organization, the Copenhagen Suborbitals, but then there are the sponsors from the most illustrious names in Danish high-tech industry, the Viable radar and tracking, the same with the Therma star cameras, the Trane, the satellite phones, etc. And, as I mentioned, the Royal Danish Navy with all of their patrol ships keep, and not to mention the owners of this, the place we are now. Right now, the test facility, the grounds where the test facilities are, the Reda, the company that owns this would be or used to be shipyard of the Burmester and Wayne. It's still a nice day. I think the wind is picking up a bit, judging. Yeah, we're probably 10, 12 knots now, 5, 6 meters. It's very open out here. Actually, in a way, it's like being at sea. So you feel the wind more strongly. Out here, it's a landfill. Actually, there only used to be a sort of a fortification part of the ancient defense fortifications of the city of Copenhagen, but it's a long time ago. It was all the landfill was filled. The shallow waters around here were filled up. But as late as 1807, this exact location we are in actually was in the middle of the great sea battle between King Frederik VI of Denmark and Lord Nelson of the Royal Navy. And King Frederik almost made it, but only almost. So this is a place of adventure, of shipbuilding, of warfare, of great history being written. Actually, in the shipyard, the company that used to own this place, that built not only ship but also huge diesel engines, pioneered the use of diesel engines on ships. But also in some of the buildings in here, some of the high-tech departments of the old rust industry here, the first functioning aeroplane in Denmark was constructed in 1906. So this is a cradle of high-tech engineering of Denmark and of Scandinavia. We're right in the middle. So it is it's a day of beauty of this volunteer, this band of brothers and sisters, young people who love technology and love to reach for the star and love to go out there and look back on our blue earth, actually do something about it, and actually are going to test their first liquid fueled rocket engine. Now it will be, yes, in 1 hour and 20 minutes according to plan, as we know it right now.
And the text at the bottom of the screen right now says in roughly 2 hours. Again, the last thing we heard was that the launch will take place roughly 1 hour after the beginning of the loading of the liquid oxygen, and that has, as far as we can tell, not begun yet. But inside our recreational vehicle, we now have Flemming Nybo with us here. Flemming is also one of the people who are very, very close to all the technical details in the project. So we're going to provide him with a headset and a microphone so that you can hear what he's saying. Yes, and Flemming Nybo, welcome aboard.
Thank you.
What's your role in the project?
I'm working with guidance, and obviously we are not going to steer the rocket anywhere today, but this serves as an opportunity for us to test the jet vanes that we will use for steering and flight. So under the rocket right now, we just mounted 2 jet vanes, candidates for flight jet vanes, but we'll see how they perform.
Yeah, Jonas told us a little bit about them earlier on, and I can understand that they're moved by servo motors and they can move pretty fast.
Well, one of them can. One of them is rigged to a servo motor. Again, a flight candidate if it passes this test. It moves from plus to minus 15 degrees, which are the extreme angles of the jet vanes. It does that in about a quarter second, and we believe that is fast enough to balance the rocket.
But you're measuring, in this test, you're measuring the drag forces and the temperature of the jet vanes, and those measurements are going to be used in the software that's going to control the rocket when it flies. Can you tell us a little bit about what considerations are there when you write guidance software for a rocket?
The main consideration is if the rocket needs a course, a steering correction. The computer will compute an amount of force that it needs to make that correction. And what we're doing today is we turn one of these jet vanes forth and back. We so to speak, we wave it in the jet, and then we measure the force that it exerts sideways. So we can construct from these data like a lookup table, so that in flight, when the computer needs a steering force of say 100 newtons, then it knows from this experiment today how many degrees it should turn the jet vane to achieve that.
But won't the force that you make with the jet vane is proportional to the thrust, isn't it?
It is. Chamber pressure from the motor is also measured today and measured in flight, and it means that the lookup table is, you're absolutely correct, actually force as a function of jet vane angle and chamber pressure. And we expect a fairly linear relation to chamber pressure. We saw that on the Sapphire rocket too, but possibly a not so linear relation to jet vane angle. And that's okay as long as we can map it and correct for this in flight.
For those of you just joining us, we're here with Flemming Nybo, who is the guidance man in Copenhagen Suborbitals. And Flemming, you were the man behind the extremely straight flight of the Sapphire rocket last summer. How much was it the rocket had drifted? 8 meters sideways when it peaked at 8 kilometers?
No, well, it was actually more than that, but you're right, we were quite happy with it. At the time of MECO, where we don't have any steering force left because there's no thrust, the guidance system indicated it had drifted 70 some meters, and then since after that there's actually no trajectory control. It keeps deviating, and at MECO at 8 kilometers it was deviated by I think 180 or 190 meters, but that's still very good and good enough for us. The 180 meters at MECO are actually verified not only by the navigation system itself, but also by GPS, so we can trust that.
Very nice. So, what's your role in today's test? What are you going to do today?
So today, shortly before the engine is started, I start a sequence where one of the jet vanes turns forth and back to its extreme angles. I actually turn it a bit further today. I turn it to plus minus 20 degrees. This is just to see what happens. It does not necessarily produce much extra force, but instead of guessing, we give it a try and see. So it waves forth and back at every 1.5 seconds. It simply does wave to one extreme angle and to the other back to center. It stays at center for a while, and then it repeats. So today I'll simply start this sequence. I will look at the data and log the data, and then afterwards I go home and do the math and construct the lookup table we need for flight.
Once you've accomplished so straight a flight that the Sapphire rocket was, you've written all this software and you've proven that it works. What are the challenges in stepping up in rocket size? I mean, it's the control job is exactly the same, isn't it? The rocket's just bigger.
That is correct. The basic architecture of the software can be reused. The precision needs to be improved because we fly to higher altitude. We would be drifting too much if we use the exact guidance system from Sapphire. So we use a higher grade inertial measurement unit this time. Except for that, I would say that the jet vanes themselves, the redesign and the scale up of the jet vanes is basically the biggest task in scaling the guidance system from Sapphire to HEAT. So this is why today is actually a very important milestone. If the vanes can stand this test, and if they can produce a good steering power, then I would say we have passed the biggest milestone in the transition of the guidance system from Sapphire to HEAT.
So this test is basically to give you input for your guidance software for the HEAT-2X rocket.
Yes.
Later on, of course, the ultimate goal of this project is to launch Peter Madsen into space, and that's going to take place in a capsule, and therefore also in a rocket with a diameter of 1600 millimeters. I suppose that once we step up to that size, you will need to do some measurements again in a static test.
Certainly, yes. So jet vanes will most likely have to be scaled up once again. So we do that. The good thing is that while the Sapphire rocket was relied on using the biggest RCE servos we could get, we now had to redesign it because obviously there was nothing bigger. And we now have a plain DC motor with a worm gear, and we placed our own encoder on that. We basically built our own servo from a standard DC motor, and that concept is very scalable. So that itself is a small preparation for a bigger future.
Can you tell us a little bit about the hardware that your guidance software runs on?
Yes, the guidance this time runs on what we call the CS2Eno. It's basically our own version of the Arduino, known as it's Arduino Duo, I think, but it has more I/O and NAND flash storage. It is designed and built by Bo Brandstrup. So he basically provides us with this brilliant hardware platform that is tailored for our needs.
Very nice, the CS2Eno. So what are your expectations today? Do you have any fears? What's the worst that could happen? What's the best that could happen?
The worst that could happen is if I have if some lame technical fault in software or hardware would prevent us from getting our data. That's absolutely the worst thing that can happen. It's much worse than if we get data and the steering force is not adequate, for instance, because then we can deal with that. But loss of measurement data is the worst thing that can happen. So I have done what I can to make the system safe. The measurement data are stored locally on the CS2Eno, which is on the test platform, and at the same time transmitted via a serial link to my laptop in the bunker at 70 meters range. So since data is stored in in both locations simultaneously, I think there's a good chance that we will keep it, even if my computer crashes. That can obviously happen. Or if, say, there's a fire on the platform post-burn that destroys the local computer there.
So, but data is downlinked from the rocket on today's test via a serial cable.
Yes, that's right. It's an IS-422 cable that I simply laid down on the ground.
So we're not testing radio downlink today.
We could. I'm not sure if the radio is operational for that or not. I don't think it is actually. But even if it was, and with my greatest respect to our brilliant radio designers, I would prefer a cable, simply to avoid any packet loss.
Well, thank you very much, Flemming Nyborg. You've listened to Flemming Nyborg, who is guidance specialist here in Copenhagen Suborbitals, explain about the measurements today and the guidance system. And good luck, Flemming, with the test today.
Thank you, Steen.
Yeah. That was Flemming. Yeah. His job is like you have to balance a 300 kilo stick on a finger and run with all of your efforts up 1,000 flights of stairs. Basically. This is the most crazy part of rocketry. This thing, how do you get it to stand on its end? I mean, that's the first thing you ask as a kid when you see a rocket. How do you do it without falling over? And that's you have these little vanes that are fluttering like wings, and he's saying it's in the jet. What I mean, it's that is inside the exhaust, in that howling flame coming out of the bottom of the rocket, with all of these beautiful things that that is impressive that a guy like that works here for free. That is. That
certainly is,
yeah.
and I suppose that guidance is the reason that people refer to rocket science as something that is very, very tough.
Yeah.
Because mixing alcohol and oxygen together and putting it on fire is not as difficult as making such a huge machine balance on its end.
Yeah. Balance just this one with the diameter, what is it? It is
60 centimeters.
60
diameter.
centimeters. That's like a big pizza pan or something like that, a big wok or something like that. And then it is 20 meters tall, it weighs 300 kilos fully loaded. It has to stand on its end. Otherwise, 100,000 horsepower is just gonna, it's gonna be crazy. It's probably going to look fantastic if it tilts, but it won't. I mean, but that's in the classic films. That was the guidance that didn't work.
Yep.
The classic films from Cape Canaveral in the early '60s, they simply couldn't get it right, of actually balancing this stick on their finger.
That is the tough part.
Yeah.
But then again, Flemming Nybo demonstrated last summer that he's capable of.
He could do it.
And Copenhagen Suborbitals is capable of launching guided rockets.
Yeah.
Not only guided, but very, very well guided.
Yeah, like you said, like the drift was 70 meters or
70
something.
70 meters sideways out of 8 kilometers in altitude. That's very impressive.
Yeah, exactly. And for a first go, and with a yearly budget of sort of minus, it's sort of it's collections. It is donations, and it's volunteer work. They can do things like that. That is what we're all dreaming about. That's why Copenhagen Suborbitals enjoy such fantastic affection, one would almost say. It's not only they have a great brand value, people love them, because there's no way you can be sarcastic or deconstructivistic or anything about something as beautiful as this. So it is a piece of art. There's this component of beauty that makes everybody smile and everybody happy, even though we're playing with big engines and big horsepower that usually make people a bit afraid.
Precisely, and I think that's also one of the things that sets this project apart from many other hobby spare time rocket projects, that it has a substantial aesthetic feel to it. I mean, there's been thought about what colors to paint the rocket. There's been thought about what font to use to write the name of the rocket. There's been thought about what colors to paint the capsule on top of the rocket, which isn't there today. So there's a lot of thought about the aesthetics.
Yeah, and there's always and the communication is always well made in the sense that it has a genuine outreach. There's never every word that's written somehow somebody meant it, and that is very, very nice reading the blogs and the website and so on. And I suppose that's why, and I hope that's why everybody. By the way, everybody out there, remember you can actually donate at COPSUB. COPSUB.com. COPSUB.com. Okay, yeah, det kan vi godt se. Yep.
We have just heard that loading of liquid oxygen is just about to commence, and as you can see right now, people working on the bottom of the rocket right now. I really can't see who it is or what they're doing, but
it looks like Peter, isn't it? Peter working exactly right. Say again.
They're installing the igniter.
Okay.
Which is going to ignite the fuel before the liquid oxygen is going to be blown down through the combustion chamber.
Yeah, so they are installing the igniter prior to tanking, to fueling with liquid oxygen.
So for those of you just joining us, I'm Sten Eiler Jørgensen.
And I'm Jan Haugaard, and we are reporting to you from the test firing of the new rocket engine HEAT-2X of the Copenhagen Suborbitals.
Suborbitals. And we, as we just told, we've just heard that loading of the liquid oxygen will begin shortly, and also we know that once the loading of the liquid oxygen begins, there will be approximately 1 hour till launch. So we are hopefully looking at somewhere in the vicinity of 1 hour until that they're going to press the button and ignite the rocket engine. And of course the rocket, which looks like a rocket because it is a rocket and it's been built as a rocket, but it will not leave the pad unless some fault has been at play. The rocket is supposed to stay on the test stand. This is a static test, and we're supposed to measure a lot of things during the burn, during the 90-second burn of this liquid-fueled rocket engine, which is going to be used for the real flight of the rocket, which will take place this summer, hopefully in August or September. And this rocket will, if everything goes as planned, actually be able to reach an altitude of more than 100 kilometers, which is the defined limit for space. So this is actually a space rocket. It will be able to make a suborbital flight into space.
Yes, it is a space bird that has been chained to Earth, actually, and its formidable engine will, at the start of this burn cycle of 90 seconds, at the start of that, it will develop a force equivalent to 100,000 horsepowers. And in that sense, well, this is that is quite incredible, simply because in that sense this engine is a very small one, right next to the launch or the test facility are one of the major power plants of Copenhagen, and one block of this power plant it produces less power than the rocket does for the beginning of this firing cycle. They are installing the ignition, yes, that is being done. The area is being clear. There doesn't seem to be any tourists around. It's hard hat area now.
We just had a question on Twitter why the launch was postponed, and of course I can understand that everybody asked that. The launch was originally planned for 1400 hours Danish time, which is 1200 hours UTC. The launch was postponed because of problems with the valves, both the fuel valve and the liquid oxygen valve, which are supposed to control the flow of alcohol and oxygen into the combustion chamber. They were found to be well, actually I don't know, but there was a problem with both valves, and they had to be replaced, or
the gaskets had to be replaced.
The gaskets had to be replaced in the valves. So that took some time. As you can see right now, people are still working on the rocket, and again, the last thing we heard was that the loading of liquid oxygen will hopefully begin shortly.
Yeah, it's still a nice day, very beautiful day, slightly more overcast, but that should clear around 3 o'clock, at around 1500 hours. There is a nice breeze, a wind, light wind blowing, I think about 6 or 8 knots. It is a beautiful day for this thing, and lots of people are outside to watch this 90 seconds spectacular of the 100th of the HEAT-2X engine going off. There's a tradition of this being really something.
Yes, certainly.
These tests out here. It's not the first time. There's been many tests here before.
Yes, yes. We've had tests of rockets since I believe they started in 2008.
Yeah.
With the first small hybrid motors, which has then been scaled up, and this is by far the largest one ever to be tested.
Yeah, and it is. We have to stress it is the next level of the great vision of the Copenhagen Suborbitals of actually sending a rocket into a suborbital run into space and returning its pilot safely to Earth. And it's been growing and getting better and better in every way. And now Copenhagen Suborbitals are graduating into liquid propelled. What is it called? You call
Liquid
it
propellant.
liquid propellant rocket. Yeah, we've got to get these things right in English. Until now, it's been hybrids. That is, that the propellant has been solid. So it's been wax. The stearine. It's been polyurethane
and paraffin and rubber and. What has more been used? Lots of different.
Yeah, lots of
fuel
anything that might burn,
combinations.
basically, one
Yeah.
could say, or has high burning value.
Yeah.
And one could say, and you had this. It's basically sort of a candle, a hollow candle, and you blow liquid oxygen through it, and you ignite it. And that was actually done by pyrotechnics. That is sort of a rockets, like the New Year
Like
fireworks.
rockets,
Yeah. But now it's the next level. It's a level of Goddard. It's a level of Karaljov. It's a level of Werner von Braun. It's the big Apollo era. This is actually liquid propellant rockets.
This is the way the professionals do it.
Yeah. This is the way you do it if you want to lift heavy loads.
If you really want to go to space.
Yeah. If you want to reach that, we have to reach a speed of up towards 10,000 kilometers an hour to do the suborbital sort of. It is a sort of a loop, one could say. We're going up and we're going diving back again. It's like Alan Shepard, the first American to leave Earth, leave the gravity for a little while. That it was actually quite humiliating at the time for the Americans, because the Ruskies had actually gone outside with Gagarin. Gagarin had attained escape velocity, which is considerably faster. That is 28,000, as far as I remember.
Orbital velocity for low Earth orbit is 28,000 kilometers per hour.
Per hour, yeah. And what will we do for Peter? It actually is Peter Madsen, founder of Copenhagen Suborbitals, who's supposed to go out there. That's his vision. That he'll has to be 10,000 kilometers an hour, something like that, to do a suborbital jump.
Honestly, I don't know what the burnout velocity of this rocket will be. Originally, of course, this rocket is now they've decided to go with guidance, do it with a guided rocket. The original plan when Copenhagen Suborbitals was founded was to launch a man inside a vehicle no wider than 60 centimeters.
Yeah.
So the astronaut should actually be standing on his feet, and do that furthermore on an unguided hybrid rocket, which was very unusual at the time. Now, it was actually the launch of the HEAT-1X rocket with the Tycho Brahe spacecraft on top of it that proved that launching unguided hybrids is difficult.
Yeah.
I believe the rocket flew 2 kilometers up and 8 kilometers downrange.
Yeah,
So-
and it was pretty scary, actually.
Yeah.
You wanted to put it very nicely, and that brings you to the conclusions that you need, just like we talked about with Fleming, like you talked about before, you need that guidance, but which is extremely complicated.
Yeah.
That is the rocket science, like we talked about
Precisely.
earlier. Yeah, this thing of running up a stair with a 300 kilo heavy stick on your finger and not dropping it.
So guidance was necessary.
Yeah. Now you can see let's see. Yeah, we have a shot from the south here. You can see this sort of you can figure out in the center below the rocket, in between the concrete constructions, you can actually see this sort of slide. What do you call it? Rutsjebane. You call it?
The water slide.
Yeah, the ramp, sort of a ramp. You know, that will be flooded with water as the engine fires.
You can actually see a pool of water around the ramp right now from an earlier test.
Yeah. Which adds a fantastic spectacle to the scene, because there will be something. There must be something like a cubic meter, 1,000 liters of water. 1,000 liters of water a second or something like that, coming out to dampen vibrations and the heat, the crazy heat coming out of the exhaust of this. We're talking, it's like a welding flame. It's very hot.
Very hot. Yeah.
So so it doesn't completely demolish even the heavy reinforced concrete below the rocket. So you can see that slide. It's on the big fire launching facilities in Russia, in Kazakhstan, and over at Cape Canaveral. That is the fantastic sort of piece of architecture just to look at.
Amazing.
Yeah. And this is done against vibrations and against heat, simply to dampen the exhaust, one could say. Right. And also to deflect it. I mean, simply just
so it doesn't
come down and
into the ground, but
come out horizontally. Yeah.
As Peter Madsen wrote in a technical blog on the Engineer website some days ago, hybrids and solids can be tested horizontally, but of course a liquid fuel rocket must be tested vertically, or you would need to build the tanks in a different way so that the liquid fuel and oxidizer can be sucked up from the bottom of the tank. So liquid rockets are much easier to test vertically.
Yeah, basically because you need gravity just to keep it at the bottom and keep it. It's like emptying an old-fashioned coffee pot. You know, I mean, you couldn't get all of it out. You know, emptying a can of beer. You know, there's always a little residue lying at the bottom. You know, but when it's standing on top, the whole thing would drain clear. Yeah.
We have a question on Twitter from Tom Lange, who asks if the HEAT-2X rocket will be reusable after this summer's launch. And as we explained earlier, that is the beauty of liquid fuel rocket engines, that you ignite them and they run and you shut them down, and basically you can just refuel them and run them again and again. The TM65 engine has been tested 3 times before, I believe, without guidance and without being built into a rocket like it is today. But the first 2 test firings were nominal, so they could just be refueled again. The 3rd time, the wall in the nozzle actually imploded because of too high a pressure gradient inside the wall of the nozzle. The wall of the nozzle is hollow, and liquid oxygen is being circulated around in there in order to cool the nozzle skirt down so it doesn't melt. And there was too high a pressure inside of that, so it actually imploded and destroyed the engine. So they've built a new one, which is this one, and it's going to be tested today. Yeah.
So there is one could say, use a word from politics. There's a system of checks and balances in rocket engines, that they get very hot, but they also carry very cold fuel. You can use that fuel to cool some of it down. It's I mean, in that way it has the same problems as all combustion engines. It has to be, you have to be careful that it doesn't overheat, of course, and that is a balance that's extremely delicate, because the nozzle is a very, very carefully crafted component.
Certainly.
and
needs-
very
it needs to
precious, also
perform.
very
Oh,
expensive,
yes.
basically.
It really needs to perform, and if you have too high a pressure gradient across those walls, they will just bend
Yeah.
because the steel isn't really that thick.
No, it's not panzer, of course, and it's not armor in any way. There's nothing inside a rocket that can be armored. I mean, everybody knows about a propane, a tank of propane gas, and you could say that this rocket has sort of gas propane tanks inside it, but one thing is very different, is that these tanks can't be made from cast or solid iron the same way. It would never fly that way. So the thickness of the tanks has to be minimized to the extreme. It has to lose as much weight as possible. That is with all components. There's a weight factor with everything. You can't just sort of squander weight in any way.
Certainly not in a rocket.
No.
Certainly not. You really
It's the same in all kinds of aerospace. That is a trade where you never talk lightly about weight. Yeah. But it's very interesting to see how the components have to be tooled and manufactured and so on. Actually, there's a lot. It's very funny. This high-tech industry there's a lot of craftsmanship in it, actually.
Oh yes.
Yeah.
Certainly.
A lot of very, very talented people here with good hands and good eyes. Have to be brought in here. Who have the people who come here have good hands and good eyes and a lot of theoretical background. That is a beautiful combination.
Certainly.
Yeah.
Certainly. We also had another question on Twitter here. Let me see. Remember, you can tweet us using the hashtag HEAT-2X. That's HEAT-2X, and we try to follow up on tweets as they come in. The first one is we have a correction from Jens Krabbe, who says the flame detector uses 20 tons of water per minute. That's 300 liters per second.
Okay.
So
1/3 of a
liters,
cubic meter.
A third of a cubic meter every second. The water sound suppression system guzzles up. And we also have a question from Jan Krüger, who asks, what is the current ETA of ignition today? We just passed 1400. Yes, we passed 1400 Danish time, but we did not pass 1400 UTC. I believe that we have still, the last thing we've heard, 1 hour and 15 minutes from now is the last word. So that is around 15:30 Danish time, which is 13:30 UTC. So last thing we've heard is that we are looking at a test time of 1330 hours UTC, an hour and 15 minutes from now. As you can see, people working currently, still working on the rocket at some time.
But we do not yet see the telltale wisps of oxygen vapor that is boiling off. So they haven't commenced yet the pumping of the liquid oxygen. And you can also see, yes, on this picture you can see there's a TV crew close by. And that wouldn't be permitted once the oxygen starts flowing. So estimated time of burn. What's ETB? Estimated time of burn will be 75 minutes from now. 1 hour and 1 hour and 15 minutes from now. But that means probably it's going to happen pretty soon. It looks as if they're finished with installing the igniter. Yep.
It looks that way.
Yeah. But the picture that is on air now, they are around the liquid oxygen tanks right now.
Yeah.
So maybe there's just some final words.
But as you can see, we still have a camera crew out there.
Yeah.
And they will of course have to go before the loading of the liquid oxygen. And as you can see on your screen right now, it says in the bottom, loading of liquid oxygen will start in a few minutes. That is not a fact, that is a hope. That is, at least that's what I hope, that the loading of the liquid oxygen will start in a few minutes. We're back here from the recreational vehicle with a lot of screens and wires inside of it. The Copenhagen Suborbitals support stream team is in place, and in front of me right now I have a mixer board where I can change a lot of settings with regard to the audio. I'm not going to touch that because I wouldn't be knowing what I was doing. I also have a screen where I can see 5 different video streams, and you are currently being served a view of the business end of the HEAT-2X rocket with people running around and working on it. And for those of you just joining us, we are of course awaiting the ignition of the HEAT-2X rocket engine, or rather the HEAT-2X rocket with the TM65LE rocket engine at the bottom. And currently we're waiting the loading of liquid oxygen, and once the loading of liquid oxygen has begun, there's supposed to be in the vicinity of 1 hour till ignition, so we are still probably a little more than an hour away from ignition of the rocket. Right now I have a visitor here in the camping vehicle here. Morten Bulskov, welcome. You are logistics officer here in Copenhagen Suborbitals, and you're a member of the board. And can you tell us a little bit about what is your job here today?
I have a general job today of making sure that all the fixed cameras are running, all the data we are trying to recover from this tests. So we have right now to set up 2 high-speed cameras in the bottom. The view you actually see right now, there are 2 high-speed cameras up there focusing on the rodders, because we need to see how they cope with the 90-second burn. Also on top of the test stand we have a normal HD camera filming down the rocket, the same view you actually have as a stream as well. And then we have some cameras covering the flame deflector, so we can see how the whole stack is doing during the test.
And the flame detector, the flame deflector is the slippery slide, the water slide at the bottom of the test stand, and that is there to make sure that this test stand doesn't melt or blow away, right?
Yeah, it is. It has a dual purpose. Of course, it directs the flame when it hits it. It turns it about 90 degrees, so it don't go directly into the earth and just will create a big cloud of dust. So it turns it 90 degrees, and in order to make sure that it doesn't melt, you put a lot of water out there. As the water has a dual purpose. It lowers the temperature and makes sure it doesn't melt, and it has the capacity to just take a little bit of the sound as well. It's not as much as you see in NASA videos, because we have the water a little bit lower down, so for us it's more temperature. But the 2 engine pumps will deliver about 200 liters a second each, so the whole area will, in the 90-second burn, there's a little bit of pressure loss, so it will probably, there will end up being about 25,000 liters of water out there.
25,000 liters of water, that's 25 tons of water released over a period of 90 seconds. That's a lot of water. I've been told that I can ask you a lot of questions about safety. Is that true?
Yeah, I've been a part of pretty much everything for the last 3 or 4 months.
I think the primary question that people ask themselves when they see this setup and hear that the rocket is bolted to this test stand so that it doesn't fly, are you absolutely sure that the rocket will stay in place?
I am absolutely sure that the rocket will stay in place. The bottom, as you can see on the pictures, there are 4 bolt anchors in the bottom of the rocket. That is the primary hold down. That is the same hold down we will use on Sputnik when we will launch the rocket. Then we also have, as you probably can see in the pictures, about 4 chains. They are mounted on this belt you can see around the middle of the rocket. It has a dual purpose. Of course, it's a hold down, and it's also to make it stable so it doesn't start to to vibrate too much, and it's not so much during the burn, but just because it's been up there for about 1.5 weeks now, so we wanted to make sure that the wind didn't do anything to it. So right now we have the capability to hold down about 15-20 tons, and the rocket will make a maximum delirium thrust about 6.5 tons. So it will go nowhere unless something catastrophic happens.
And these anchors, they're then attached to the test stand, I suppose.
The whole the structure that you see people walking around is actually a very big iron structure, weighing in at about, I think it's about 10 tons. 6 tons, and that is mounted on top of the first layer of stones that you see. This structure is then fixed down the sides with some very thick metal strips that are bolted into the stones, about 4 or 5 anchors per one of these strips. So the whole test stand is actually bolted together. So if you would try to lift it, you would try to lift 160 tons. Because we're testing a finished rocket, we had to put these extra 3x3 stones we have on top as well, because in the old test stand we tested the engine below. It was mounted further down, but because we have a full rocket here, we had to put in some extra protection on top, and that is why you have these 3x3 stones. If something happens, a catastrophic engine explosion, the debris will primarily go either up or towards the bank that we see in front of the test stand, so it won't hurt anybody.
So there's a reason that the test stand is angled so that people actually, or the people who are here today, actually can't see the rocket engine itself once it runs.
No, they can't. We make sure that everyone is standing behind the line of the front of the test stand, and it's a security precaution. The only thing we have in front of it that can see in is actually the command bunker, the mission control bunker, and where we do some photographs as well. And that is also made of the same stones, and they're 80 centimeters thick. So we have the possibility to look out through slides in there, so we can actually see what's happening with the engine. But that is the only place where we can actually see the rocket, and we can't even see it that good because the angle is decreased a lot because of the slope in front of it.
So for security measures, people watching this on YouTube right now actually have a better view of the test than the people who are actually here.
Yeah, that is correct. What you get when you're out here is more sound. You get the whole picture. You of course will be able to see, because the flame deflector directs the flame in a 90-degree turn, you can see the end of it, but you can't see the actual nozzle of the rocket. So when you're watching on video, you will see a lot more. But out here we have an expectation from the other tests that the sound will be quite high, and it will actually reflect from the building just behind the public, so they will get it double.
So it might be difficult to see from these pictures, but right in the line of exhaust from the rocket, there's actually an artificial hill, a long artificial hill, yeah, behind, so that we won't have any ejecta sent that way. What's on the other side of that hill?
Right on the other side of the hill there is a road that we cut off when we run the test. For those 90 seconds we're going to close that road for a bit, and behind that is some grassy fields, and then we have the ocean.
Well, that sounds pretty secure to me.
It is the best that we can do compared to that we're actually more or less in the middle of Copenhagen.
Yes, that is interesting. A test of a rocket engine right in the middle of Copenhagen. That is interesting, but it looks like everything has been thought about.
We have made sure that the building that is actually behind the test stand on the other side of the dock is also evacuated. They are joining the general public up here. We invite them up to get a soda and maybe something to eat, so they can enjoy the test as well, because we don't want anyone to be there. If we have some kind of engine explosion, you can have a ballistic piece of shrapnel that just goes through the roof, and we don't want that to happen.
You also have this this cap on today that's called crowd control. Is that right?
Yeah, I helped Christian Elof with a little bit of the crowd control.
Well, wait, can you tell us about that? How do you control a crowd?
Well, we have some very nice guests, so they usually do what we tell them. But basically, it is like we do it at music festivals and the like, where you put up some little bit of fencing and some guide wires so people know where they have to be, and you just make sure that they stay within that, and then you place some guards that they can direct their questions to if they have any, and it is not a big problem because people want to be secure and they want to see it out here. So we have two kinds of guards. We have the guy standing with the crowd and just being sure that they are safe, and if something happened they can help evacuate them, so get them out of the area. And then we have the ones that will close off the road for the 90-second burn. And then we have a couple of people placed in strategic positions so they can actually see if someone with a dog suddenly wanders into the area.
And of course you sell sandwiches and hot dogs so that we make sure that people are around there.
Yeah, we make sure that the best place to actually watch the test is where they want to be, because you can't really put them anywhere else. There isn't room for anywhere else to see the rocket as good as you can from where the public is standing.
So what's your job during the next hour? What are you doing right now? What are you going to be doing during the burn?
During the burn I will act as a photographer, still photographer. I will take some pictures from the bunker. At T-minus 15 seconds, where we pressurize the rocket, we will begin to start the cameras. They can roll for about half an hour. So we will go out and start them up. We're 3 guys doing that. We have one starting the cameras on the platform, and then we're 2 guys starting the cameras on the ground level. When that's done, I revert to being a normal photographer and just stay in the bunker. And when the burn is finished, we will go out and make sure that we recover all the data and get it copied to computers, so we actually have something to use. And it has a dual purpose. Of course, we want to make the nice and cool videos that we see on YouTube, and then we can, the very important high-speed footage is to determine how well the rudders actually manage to do the test.
Very good. Morten Bulskov, Logistics Officer, thank you very much for joining us here and telling us about your tasks today. I hope you have a good test, and thank you very much, and
You're
see
welcome.
you later.
Okay, we'll see you later.
And once again, for those of you just joining us, we've just talked to Logistics Officer Morten Bulskov, who is of course a busy man, but thankfully he had 10 minutes to talk to us here now. And again, we are awaiting the commencing of the loading of the liquid oxygen, and we've been told that once the loading of the liquid oxygen has begun, the launch will be 1 hour away. Now at this time it does not appear that the loading of the liquid oxygen has begun yet. You would of course see liquid oxygen boiling off. A small vein of vapor would be visible, so liquid oxygen loading has probably not yet begun. We currently don't know why yet, but we will try to find out soon enough, and of course we'll tell you once we know.
Mads Wilson, hvor er din henne?
hallo?
Hallo, vi er i gang med
Ja.
Jørgen her. Det er bare lige op 5 minutter indtil vi lukker så.
Thomas, flight, kan du lige komme her rundt om det? Front. Radio. Thomas, det er Peter op fra testcellen. Kom ind. Ja, Thomas. Vi har haft de her bekymringer omkring fugtighed i systemet, og de kan stadigvæk være aktuelle, men der er en interessant detalje her. Påfyldningsventilen, den er nøjagtig samme type som hovedventilen. Den har været udsat for det samme miljø her i går omkring potentiel at der kom fugtighed i den. Og den kan manuelt opereres, og den går så let som nogensinde. Skifter og ud. Jamen, det er jo godt ikke, Peter. Tak. Det er alting meget fint ud heroppe. Der er fuld flow. Vi har en lille bitte lokslækage, men den er så lille, så det ikke er værd at snakke om. Men ellers er der fuld flow på det her.
Well, it's a beautiful day here in Copenhagen. There's a light wind, about 6, 7, 8 meters per second. That is 10 to 14 knots. It's slightly overcast, but it's wonderfully warm. Actually, it is officially the last day of spring. No, the next to the last day of... No, it's the 31st of May. It's the last official day of spring. Tomorrow it will be officially be summer. In summer here in the north, with the white nights and the girls howling in the woods. We are here in Copenhagen testing the new rocket engine of the Copenhagen Suborbitals. It is called the HEAT-2X. It's a liquid propellant rocket. It's the new level for Copenhagen Suborbitals. They're sort of going into the league of the grown-ups. This is an important day in many ways. There's a lot of systems to be tested, and in a few minutes we'll have some of the electronic guys coming in. Copenhagen Suborbitals is an interesting organization. It's completely voluntary, non-profit in every way, but still manned with some of the most talented people who are able to produce some of the most complicated modern high technology and components for the rocket.
Okay, here's a report from VTC3. The status on VTC3 right now is that we are loading oxygen from 3 tanks. We have so far loaded about 600 kilos of oxygen into the HEAT-2X launch vehicle, and a substantial amount of that, of course, evaporates in the chilling process of the rocket.
Hello,
but we can now see the whole oxygen tank covered with ice, which is an indication that it's way below the freezing point of water.
This time with Sten Andersen, who is
there has been some concern as to the
flight dynamics
possibility that water moisture might be in our pipelines. There's been a glitch which may have allowed water to be in the moisture to be in the pipeline, and this has caused some concern at the test stand. However, we have been tackling the fill valve on the rocket that's been exposed to the same environment, and it operates just nicely. And since it's the same type of valve as the main valve, and since it operates beautifully,
sounds like the
we have
software
decided
you're
to
writing
go
is
on
the most mission critical
with the preparation, with this indication that everything is fine.
It has to work, yes, but everything has to work in connection. So
what it does is that it means that when we reach the moment of ignition, the concern of whether or not we will see the valves open as they are designed to do, or we will have a stock valve, as some might remember from 2010,
is both to control,
will be intense.
but also to
we are hoping and we're praying for a non-stock valve, and we'll find out in
doing the
some time.
the engine
As I mentioned, we are now loading oxygen, and we are 600 kilos into the run, and I would expect us to need to load about 1,200 kilos of oxygen in order to chill down the rocket and all its things. And that means we're just about halfway or just past halfway, and we've been loading for about an hour.
By doing this,
so we are maybe in the order of an hour from finished loading oxygen.
Minutes prior to T0. And then the engine controller.
Any other thing that we can think of on the rocket is in excellent condition. There's only this little concern with moisture in the system. And we've seen, as mentioned, a valve in the same environment working okay. So there's good hope for a nice test.
And then you also you measure pressures inside the engine.
Yes, we have. We read the pressure in the fuel tanks, and just before the inlet to the injector, and then we have 2 readings, one redundant for in the chamber.
And as far as I've been told, we're pressurizing the 2 tanks to somewhere around 20 bars. What kind of chamber pressure are you expecting?
It should be around 15 bars.
15 bar chamber pressure today.
Yes. In the beginning, it's a pressure blow down, so the pressure in the chamber will go down gradually during the burn.
What sample rate are you using?
On board it's 1000 hertz, and just for the monitor it's 10 hertz.
Okay. So, and you've been doing this for the past many tests, right?
I've done this for the last
Are
there any special modifications to the software for this test?
Yeah, it's much more complicated.
Why is that?
Because we are controlling a lot of valves, and we are monitoring 6 pressures as opposed to 2 pressures, and 1 valve and 1 igniter, and so on. So it's a more complicated system. Yes.
Are you storing this data in the computer on board, or are you transmitting it somewhere?
It's stored on board, and it's stored on my computer, and all network traffic is logged. So we have a fair chance of getting the data afterwards.
You seem very calm and relaxed. Do you have everything under control since you have time to sit down and talk to me here?
Yeah, right now the logs is being loaded, and that's a process of 40 minutes or so, and afterwards we have to pressurize, and then I think I'll get nervous T-3 minutes when I'm sitting down in mission control, but I'll wait until that moment to be nervous.
I don't think you'll be the only one who will be nervous around that time.
So
Sten Andersen?
Yeah, it's a very exciting day for Copenhagen Suborbitals. I think it's the biggest and most complicated rocket in our training.
Will you be, on the grounds of the data you collect today, will you be making any changes to your software based on the results of today?
No, probably not, unless we find an error, of course. But that shouldn't be necessary. No.
Sten Andersen, FIDO and Engine Monitor, thank you very much
You're welcome.
for taking the time to talk to me here.
Yeah.
Thank you.
You're welcome.
And then beside here I also have Bo Brandstrup, who is going to put on a headset so that he can be heard on YouTube. Welcome, Bo. And tell us a little bit about your job. You're the hardware guy in the rocket, right?
Yes, the electronic hardware guy. I have made or designed our microcomputer based on an Arduino Duo design, which is open source, and I had just converted this to our use, added a lot of ports and input-output that we will need for our projects.
So you're actually the one who built the CS-Duino.
Yes, I'm the guy who put the parts together, both on the schematic and designed the circuit board, and I'm also the guy who actually mounts the boards with components, doing the soldering job.
How many CS-Duinos are there inside the rocket?
Right now there are inside there is only one. That is the engine controller. Another one is in use today in the guidance system. We are testing the guidance vanes in the jet from the engine, and Flemming Nybo, who is designing that part of the system, is using his CS-Duino, which will be the guidance computer. He's using that to collect his data from the rodders.
Well, what are the differences between the Arduino and the CS-Duino? Why did you need to make a new one?
Basically, we found out last year that mechanically the Arduino is not very well suited for our purposes. The mechanical fastening points and the holes in the circuit board is very prone to cause short circuits, and we had a short circuit which cost us several hours in the harbor in Nexø last year. So that's the first objective of making our own version, that we can trust it when it is mounted in a box. No nasty surprises from mechanical fastening.
So the CS-Duino is more mechanically robust than the Arduino?
Yes, it is. It's also like 6 or 8 times as large, the board, but that doesn't matter to us. We would rather have the large board, which won't give us any problems of mechanical kind of things.
Have you what considerations do you have in with regard to power consumption and development of heat?
That is not of major concern. The power consumption is quite low without us doing anything special in particular about that. We have on the other hand, we have installed a system which monitors the current consumption, because we are flying eventually in vacuum, and outside the atmosphere and cosmic rays and so on are prone to cause problems which will show itself as a drastically larger current draw, and then if we detect such a current draw, we shut the system down and restart it immediately.
So the CS-Duino, is that electronically completely similar to the Arduino?
The core of it's the same processor, and we program it via the Arduino interface as a serial port, which we use. We have moved the serial port, which is usually included in the Arduino board, to a separate board, because we would like to have that processor, which is outside the board, to have a one less risk of problem.
But then, when you are the hardware guy, what you have done is over now, right? I mean, what is your job here today?
Yes, I have involved myself in a lot of the thermal insulation of the cables inside the motor compartment of the rocket. We have no really good ideas about how the temperatures will develop in the motor compartment, so we have said better safe than sorry, and we have insulated all the cables from the engine controller box to its various sensors and actuators with a multi-layer insulation. It looks just like the insulation you see on satellites, this gold-colored foil, mylar foil, in several layers.
When you say the engine compartment, where is that in the rocket? Where's the electronics actually located inside the rocket?
The engine controller is sitting on top of the engine, on top of the injector shield, and that is between the engine and the bottom of the fuel tank. So that's where all the valves and actuators for turning on or turning off the fuel and the oxygen is also located.
And basically, no one has any idea how temperatures will develop in that compartment during the burn, right?
No, we of course expect that the liquid oxygen, which is minus 183 degrees centigrade, will chill everything down to very low degrees. But on the other hand, when the motor ignites and runs, how far will the temperature go up again? Will it be very warm or will it stay chilly? But of course, we have insulated the liquid oxygen fuel line as best we can. So we hope that it won't be much below 0 degrees, but we are ready for anything, really.
So what will you be doing during the burn? What's your job here today, right now?
My job is more or less terminated for today. I have fastened the last cables late this morning, and then I have just been doing small jobs, odd jobs, when somebody wants a hand with something.
So basically, you can just lean back, relax, and enjoy the show.
Yeah, more or less, yes.
Wonderful. Thank you very much. Once again, I've been talking to Bo Brandstrup, who has designed the CS Duino board, which is currently running the main computer inside the HEAT-2X rocket. And we've talked about how that is going to run. Thank you very much, Bo, for taking the time to talk to me here. And once again, for those of you just joining us, loading of liquid oxygen in the HEAT-2X rocket has begun, which means that we are less than an hour away from ignition. And of course, we're going to test the TM65LE rocket engine at the bottom of the HEAT-2X rocket, and that is going to take place with a burn that lasts for 90 seconds. Once again, we are somewhat less than an hour away, probably, from ignition, if no errors occur. But we will, of course, update you in the course of time as we gather information about how things are going along. We'll be taking a short break here, but we'll be back.
Yeah, we're coming up of the firing, the first burn of the new HEAT-2X engine of the Copenhagen Suborbitals here in Copenhagen. It's still a nice day. It's actually quite warm, but there's a wonderful breeze blowing, cooling everything down. Within the hour, we will have the burn. Right now, the fueling of the LOX, the liquid oxygen, is nearing completion, and then pressurizing will begin. We'll see in a bit more than half an hour. Meanwhile, I talked to Jørgen Jacobsen, president of the Copenhagen Suborbitals. Jørgen,
yeah, here I am.
Yeah.
I have to correct and say I'm chairman of the Copenhagen Suborbitals support organization.
No, yeah,
which is the organization that funds most of this project. We are so fortunate that we have more than 1,000 followers around the world, and each of them are donating in approximately more than $20 each month. Has done that for years, so that makes the foundation for the entire project.
Okay, yeah, that's fantastic, and it has an Copenhagen CS, as we call it, has a global following.
Yes.
Yes, and well, which is natural because space is without borders. Yes.
We started here in Denmark, but we soon began to recruit followers from around the world, and now we have, I think, about 30% of our followers are international.
Okay, that's nice. That is, yeah, we like that here in Copenhagen anyway. We like to feel international around here. But how do you join? How do you do it? I suppose you go on the net on the
website.
Yeah.
Copsub.com, of course, where you hopefully already have been once today to find the web stream that you are currently looking at. And on the right you find a button where it says support us, and please press that one. And you have several ways of donating, but you can of course use PayPal. And we like every donation. Every donation will help us reach our goal of putting a man in space, hopefully within a reasonable amount of years. But we are well on the way, and today's test will definitely be a major milestone in that effort.
Yeah, and you actually kept it up for quite a while, and the enthusiasm is still blossoming.
The enthusiasm is actually only growing. We founded the support organization in the autumn in 2010, and we rather fast got a group of, I think it was about 150 supporters in the first 2 weeks, and it has been steadily growing since then. And we are almost at 1,100 supporters right now, and that's actually a very special thing about an amateur project of this kind, that we get supporters that are regularly donating instead of just putting one-time donations.
Yeah, one-ups. Yeah,
Yeah.
but you actually have some kind of subscriptions,
Yes,
subscribers.
we do. We do.
Yeah. So you have. So let me get this right. You have a bunch of subscribers, and they do it of a good heart. It's not. There's no organization. There's no voting for chairman.
The only thing they get back is the fun of it.
Yeah.
And most of our subscribers are people who are fond of rocket science, and most like myself, I was one of the first, and I always I dreamt that I was born in the 1920s or 30s, because then I could be part of the Apollo project and look at all that. But this is the closest thing I get to doing actually rocket science. And I think all our supporters, many of them, would have liked to join us here as actually building on the rocket or be part of the daily work here. But being part of the support group is the best you can get, and you get to be part of the projects, even though you're not around.
Yeah, and it's a real thing.
It's definitely the real thing.
Yeah, because that's a nice part of it. Then you have the Copenhagen Suborbitals here, where there's a number of individuals in some kind of non-organization, driven by the personal craziness of Peter Madsen and until recently Christian von Bülow to some extent, but I mean it's a sort of a common craziness because it's not only Peter. There's a lot of very, very funny people here who at the same time are qualified almost beyond belief.
Exactly, and that's the fun part of it, because as you say, you have to be a bit crazy to be part of this project, because we're doing things that most people would say will be complete out of question. As you know, only 3 nations have put people to space until now, and there's been Russia and US and China, and India is on the way, and our goal is, well, to put Denmark on that list. And most people think we are really, really crazy, but we are only part crazy, because we're doing this by the book, and by the book is almost literally, because in the 40s and 50s and 1960s, all rocket science was really bleeding edge, but a lot of the theory has gone into textbooks since then, and even though they are quite far from textbook work to actual practical rocket science, since the theory is something you can read up to. You are quite long down that road to an actual rocket.
Yeah, and then you decide to do it, but there's also there's a lot of dead ends in the sense that a lot of the real important knowledge here is secret, confidential. When you're getting really close to talking about, like for example, we've just been talking about the guidance, about the vanes, about the little actuators. When you come to talking about the actual spacecraft, there's a lot of things, you don't just invent. You can't just read up on automatic parachutes or drogues or retro rockets and retro burns and all of these things. It's only open source to a certain extent, but you plow yourself through all of these difficulties, and then you leave behind you an open source. You actually sort of in building your rocket, you also sort of publicize the art of building rockets.
And I think that what triggers a lot of our supporters, since this is really open source, we publish most of our blueprints and the software that actually runs the rocket, and this is, as you say, something that has been kept completely secret for all commercial and governmental space programs, and this is the first time in history that real rocket science is in the public domain, and as I said, our support group is steadily growing, and I think a lot of them are around here today. We have about between 400 and 500 spectators eagerly waiting for tanking to complete. But we think they are patient, but they also know that this is rocket science, and it is very hard to plan the actual launch day. But say if we are able to test within now we say maybe
half an hour,
I think people will say it's okay. The sun is shining, and we have sold out now of our famous rocket sausages. We have one of our former board members, Jan Sørensen, who is a former champion in barbecue. He has a tradition for making rocket sausages and for our events, and he planned that he would sell about 200-300, and I think we have sold out more than 500 today. And
Yeah, but
all yeah, and then this all goes to the project. So
yeah,
so
yeah,
it's
but
very
also
good.
it is quite a thing to do, you know, on a Saturday afternoon in a big city. They can actually go and watch a rocket launch. I once went to one at Cape Canaveral, and you could that was a bit of the same thing, but it was a very long way from Orlando down there. Here you can actually take the harbor bus. And well, it's actually within the city of Copenhagen.
It is right, just a walk in the park.
Yeah, yeah. So and there's a very nice atmosphere outside here. I can only say that, and everybody's waiting for this liquid oxygen. And maybe repeat, why does it have to have liquid oxygen, since it's already full of high explosive or highly flammable alcohol? That is because that when it reaches a certain altitude, there is no more oxygen, so it has to carry its own, so to speak, its own food. It's a picnic basket, and you can see that from. You can see what is our airframe picture is from the south. Well, there we can see sort of the flame deflector and the silencer. This flame deflector is sort of a slide, and that will deflect the flame so it doesn't hammer into the concrete and sort of it will burn away the concrete, basically.
It will.
Yeah.
It will.
Yeah.
And all our spectators are around 100 meters
Yeah.
to the left of the exhaust of the engine.
Yeah.
Because since we have planned everything and we have done a very thorough test of everything, we cannot guarantee that something dramatic will not happen. So we have spectator security as our highest priority at all, and that's why we keep people at a certain distance, and the exhaust will go into the hill.
Yeah, it's sort of perpendicular to the line of sight of the spectator,
Yes.
so they won't sort of stare into the flames,
Exactly.
which could be quite exciting. But if something goes wrong, it's 100,000 horsepower that's being let loose there.
Yes, and
Yeah.
you are always able to watch the burn on our website copsop.com just after the test.
Yeah, and there will be plenty of different angles, and there will be slow-mos and even more than that, super slow and so on. Yeah.
And all the spectators today, they will also get the chance to get really close to the engine. Well, soon after the burn, when we have secured the area and secured that there are no more dangers, we'll open up the gates so that spectators can come right down to the rocket and look up into the engine, and that's really something to see. And
Yeah, to
to
see
wait
that.
for.
Yeah, and it is fantastic. It's we'll see that. You can look forward to that. It's a beautiful, beautiful piece of engineering, and when everything looks cool, everybody's cool. So there's a good vibe about this. There's probably some good karma too. This has been coming a long way, and you kept it up all the way. There is a vision. There is a vision here of the first one, the Ad Astra, going to the stars.
Absolutely.
Reach up and out.
And this is, as you have said several times, this is the first time we do a full burn, and this is something really, really special. We have had several events out here where we have tested engines in different configurations with different fuel and oxidizers, but this is really the real thing. It's upright for the, well, not first time, but it's the first time we have an actual rocket in our test stand. Normally we have had only the engine alone with separate oxidizer and fuel tanks above it, but this is the first time we have the real rocket that is actually about to fly.
Yeah, it's almost a full stack.
It is the full stack.
There is the parachute module. It's only
Exactly.
missing the spacecraft itself. Yeah,
It's a spectacular sight.
Yeah, definitely is, and that to think it has this it's a beautiful installation. It looks cool. It looks professional. But still, it's built by a bunch of volunteers
volunteers funded by other volunteers, by
by
volunteers, supporters,
by
and
good-hearted people all over the world.
Simply, you just think this is fun, and all you people out there in the world watching this, well, to be able to see this once more next year with an even bigger rocket, what you can do to make this happen is to go to copsop.com and press the support button and support whatever you like. We'll appreciate whatever you donate. We encourage people to make a regular donation. Normal fee is $20 a month, but you can donate whatever you like.
Yeah. And look at what's come out of it. It's really come a long way. I mean, and of course, I mean, to put up such a unrealistic goal, some would say crazy, but when you look at it, well, take your time, make the experiments, figure out the way around the riddles and the secrets, and in that sense, there's that in that sense, or that accounts for the good vibe. There's a relaxed atmosphere here, even though, of course, since there's a lot of volunteers, a lot of donations, also of equipment. We shouldn't forget that there's a lot of people are sort of bringing their own equipment, companies, and are donating tools.
I think what we can see now is that the LOX tanking may be finished. It looks like the LOX pipeline, the insulated silver line.
Yeah.
It could be a sign that the LOX tanking has completed.
Yeah, it's feed number 2, but is that on air?
It is on air, yeah.
Yeah. The close-up, we can see the veins of the rocket. There's a leg of somebody, maybe Peter, but there we have sort of the frozen line. So
as soon as the LOX tank has completed, the valves will be closed and pressurization will begin.
Pressurization, yes.
Yes, because the LOX for liquid oxygen, it will start to evaporate. Well, it evaporates all the time. That's smoke you can see coming out of the top of the engine, the rocket stack, and the evaporated LOX will start to build up the pressure inside the tank, and will, in the end, when we ignite and open the main valves, will push the liquid oxygen down into the engine. So that's how it works. Well, we have this concept right now where we have the pressurized engine and self-pressurization, but we also are working on
to use pumps.
To use pumps. We'll see if we get there, but the current concept is now with pressurization.
Yeah, so you sort of build up the pressure in advance, like in a bottle of propane, whatever, and a bottle like you see them in any hospital, in any kitchen, and so on.
Exactly.
And you carry that off.
Yeah.
But once it gets bigger, especially, you need pumps to keep the flow regular.
But now, while you sit there at home watching this,
or keep the flow smooth. That's more the smoothness is the word, as we discussed earlier.
And now, when you have completed the day's test and you have watched the hopefully spectacular sight, I really encourage you to take a more close look at all the feeds that we have from our former tests as well. We have tested engines in all different configurations, and if you like what you see, then please donate to the project to keep it up running and keep the project going towards really launching a man in space in the first real amateur-based space project.
Yep. Thank you, Jan.
I think that's a bit.
That's great. Yeah, this extraordinary association is worth supporting, definitely. It's a fun thing. You waste your money on so many other things. This is really nice. This is really This feels good all the way around. And the audience outside, it's a pity we don't have any pictures of the audience outside, but it's a nice family scene. It's full of kids, full of all sorts of people, of ancient white beards that are coming here who dreamt about hearing the roar when they were young, and heard about the Sputnik and the Soyuz and the Gagarin, about John Glenn, and they want to hear the roar just once before they die. You know, it's nice. Here they can. It's a real experience. This is 100% authentic. There's nothing much virtual about that. And we're coming up. I believe the pressurization actually started. The tanking of the locks is done.
The last word I heard was that passive pressurization has begun. They've shut the tank, but they've not started actively pressurizing it yet.
Yeah. So the frozen oxygen will expand as it gradually warms up, and that's what you call the passive pressurization. Then it sort of will build up pressure inside its tank, and after that you'll pull an outside compressor to it and actually give it some more.
You'll blow some gas into the tank to pressurize it, and we just heard Sten Andersen tell us some minutes ago that's going to happen at T-minus 15 seconds.
Okay.
Then
T-minus 15 seconds.
They will blow nitrogen into the fuel tank with the alcohol, and the liquid oxygen will be pressurized with helium.
Okay, that is because they are completely neutral. They won't mix with what's already inside.
Precisely.
And they build up a pressure to about 10 times the pressure of a car tire, about 20 bars.
Yes.
Is that correct? Yeah. Yeah, one can say that these tanks for alcohol and locks are also precious pieces of engineering. They're very thin walled compared to what we normally know about tank containers and flasks for propane or welding and so on. This is extremely lightweight and it still can hold very high pressure inside them. Testament to the high professional skills of the volunteers of the Copenhagen Suborbitals, of the people working here in their spare time. They actually weld this kind of actually you call them bombs in French, but and you could these tanks, they're very fine, beautiful pieces of engineering. You can probably find pictures of that at the copsub.com website of the fine engineering being done for this. It's all homemade. It's garage work basically. It's a big garage. They have a nice place to work, and they have some companies have donated some advanced equipment, some very big and very fine lathes and different kinds of equipment, but it's all handmade, made right here.
Basically, this is spaceflight. I mean, if you have a lathe and a welding apparatus and a drilling machine, you can build rockets. I guess that's basically the philosophy behind this project.
Yeah, and then you need some pretty skilled guys.
Of course you do.
Yeah. And like really skilled guys. It's not
very skilled.
Yeah. The workshop of the HEB, the assembly building, the heat assembly building, is quite unobtrusive. Very nice place, but quite unobtrusive. It's the talent of the people, the craftsmanship, and they have some pretty cool, they've done some pretty fine stuff. When you see the close-up, the what is in the picture right now, everything is handmade in the workshops of Copenhagen Suborbitals. Yes. And well, we're coming up to the firing. I think we're lucky we'll just have it hopefully before 4 o'clock. That would...
The last word was that the oxygen is on board now and the tank is closed. So I think that we can hope for an ignition within the next half hour.
Yeah. It's coming up. It's going to be quite a sight, and especially, yeah, the audio is fantastic. It's worth traveling for. So, and
precisely.
Yeah. So if you're out there on the planet and want to plan something for next spring, there probably will be a new test. And if you want to hear a real roar, come to Copenhagen.
And we are currently, how far are we away from the test stand right now? 100
meters, yeah, 120, yeah.
And I certainly expect that we will hear a low rumble.
Oh yeah, no, we'll hear the full spectrum. It is very beautiful, very, very loud. And for anyone who loves loud machines, it's...
And we just heard someone from the pad asking to get the cameras ready. So there's certainly some activity going on right now. As you can see in the pictures, we still have people working directly below the rocket engine, but
that probably isn't that adjusting the cameras, because there's a lot of, like we had explained earlier from the guidance, they need all of the information about the movements of the vanes, the actuators, all of this fine, super fine movement. They'll need a slow motion footage of that. I think it's
very important to get good footage of the thrust vanes during the burn.
Yeah, because that is how it's being guided. Now is that actually you have vanes that go into the exhaust.
Somebody needs a wrench on the pad.
Yeah, that's a good sign. Things are getting hectic, and everybody's getting in place to calibrate their measuring equipment. And yeah.
Okay, this is Peter Madsen now asking people to get ready to start the cameras.
Yeah.
So this is interesting.
The probes cameras being extremely important for keeping being extremely important in the documentation of the performance of the HEAT-2X, which now I think it's coming up. It might be soon. The test firing will have 90 seconds of 100,000 horsepower, starting out with 100,000 horsepower to be precise. It is gonna be quite a sight, and it's gonna be quite a sound for everybody. It's something that everybody should enjoy at least once in their lives.
The TM65 LE rocket engine will burn for 90 seconds, at least that's the plan. It will start out with a thrust of 56.5 kilonewtons, which is a little more than 5 metric tons of thrust, and the thrust will then decay exponentially because the tanks are pressurized.
And we're keeping up with the radio communications at the pad. It sounds exciting. Yeah.
You can't see a lot of people out there now. You can see a couple of people crawling around the rocket.
Yeah, that is the liquid oxygen line. It hasn't been disconnected yet. The umbilical That is our friend.
I didn't quite see who that was.
Det er ham, der var herinde lige før.
Yeah, yeah.
And that is Peter Madsen.
We have a view of a very nice blue and orange plastic bag.
Yes. It's two of the key personnel, Peter Madsen and our guidance man, isn't it?
We've just had a VHF radio moved into the studio here, so we can also hear what's going on. As some of you have commented, we have been speaking on top of some of the radio communication going out on the stream, as well as here on the area. So now we should be able to hear what people are saying, as you have.
Yeah, please give us feedback immediately. Things like that happen, because I mean, there's and we'll try to sort it out right away.
And you can of course comment and ask questions, and we will see it if you tweet on Twitter with the hashtag HEAT-2X, HEAT-2X, and then we can answer your questions as they come in.
Yeah, as Steen was telling a moment ago, is that the pressure of the rocket will decrease as the fuel tanks empty, but so will the weight of the rocket. So that is one of the ingenious things of a rocket, is that it might lose a bit of power, but also loses a lot of weight.
So the acceleration will remain more or less constant. Yeah.
That is, yeah, that's one of the beautiful things. That was a strange Russian rocket dreamer, Konstantin Tsiolkovsky. He was deaf, actually. He figured that one out. Even before there was anything called airplanes, he had that one figured out.
A true visionary.
Yeah, one of the great guys. And on his mathematics, everything is still built. Everybody's, and that's one of the reasons why Russia was in the game so early. That was because of him. They had this guy. So now I think, I don't know.
We can tell you about the rocket engine nozzle. It's it actually has many of the features that you see in modern commercial bipropellant rocket engines. The nozzle has a hollow skirt where liquid oxygen is being circulated to cool it down.
Yeah, that's the liquid oxygen used for the
used as oxidizer. Is a small part of it has been taken out and circulated to cool down the nozzle skirt. Also, the nozzle, in the throat of the nozzle, there are small holes where liquid oxygen is being blown out, so that the liquid oxygen will run as a thin film covering the nozzle, cooling it down as it evaporates, which is actually called film cooling. So it has film cooling, and it has circulation cooling.
And actually the actual shaping, engineering, tooling of the nozzle is almost a piece of art. It's a very, very high precision job to do that, isn't it?
Yes, it definitely is. And the shape of the nozzle is funny. It's called a de Laval nozzle after Gustav de Laval, who was actually a Swedish dairy engineer who devised this nozzle in order to work with dairy products. And I'm not sure about the validity of this, but the story goes that it's American rocket pioneer Robert Goddard who found out that a nozzle of this sort was actually extremely interesting to use as a rocket nozzle, because it's isentropic. The entropy of the gas through the nozzle is constant, so that it will lower the temperature and pressure of the gases, but you will increase the speed of the gases so that the de Laval nozzle actually maximizes the speed with which the gas leave the rocket, which is of course what you want in order to have as high a thrust as possible.
Yeah, I believe it's also used in water turbines. I think I've picked that up once. Yeah, that's quite funny. It's from a dairy inventor. That comes this, and actually, but actually dairy products, dairy production, in the late 1800s was high technology. Turbines.
Oh yes.
For all sorts, like for separating cream from milk, for example, were high technology products. You know,
Certainly.
And the ball bearings, things like that, were developed to a very high level of precision. So that's funny that these things are connected. We are now 15:45, and everybody should be a bit excited. Please give us feedback on Twitter if we are talking over any of the PA system outside. I don't know. We can't. No. Well, we can hear the PA system now.
Yes, we can. We can hear the radio communication out on the pad. Right now, we couldn't that before, but we now have a a small handheld radio standing here in our studio.
So we can monitor the
Yes.
the sound from the control room.
We just had a tweet from Free Rolling Papers asking, isn't it the alcohol that's being used for the film cooling? I actually think that is completely correct. I think I was wrong.
Okay.
I don't think it's oxygen. I think it's alcohol actually being used for the film cooling. So thank you very much, Free Rolling Papers, for pointing that out. I think you're right. It is alcohol used for the film cooling and oxygen, I believe, for the skirt cooling.
Okay, yeah.
This is going to be very spectacular. There's no doubt about that.
Yeah, and it is a fantastic piece of machinery you got to get to work. It really is a very, it's more than just a step up. It's like a quantum up from the older engines, like just the sophistication, the levels, and actually the fact that we're approaching this with all this confidence and so on.
And again, the TM65 engine has been tested 3 times before, but that was in a test configuration where you just had the engine and you had a bucket of liquid oxygen and a bucket of alcohol on top, and it was nowhere near being configured for flight. It was just a lot of pipes.
Yeah.
This time it's actually built into a rocket. Everything is streamlined and aerodynamic. It even has fins, and it has control computer, and it has parachutes on top.
Yeah. All it needs is a space module, the crew module.
Precisely.
Yeah. And actually, I mean, as we speak, another group is working with preparing the launch pad for this summer. I mean, so there's still a beautiful, very elegant kind of. There's a very elegant kind of optimism here that we're actually preparing the seaborne launch pad.
Now you can't see this, but in this recreational vehicle that we're inside is parked just outside the HAB, the horizontal assembly building. I'm just going to take a picture here of what it looks like out of our window, and I'm going to tweet it with the hashtag HEAT-2X, so that you can see that we're actually looking out on the new center hull of the Sputnik floating launch platform that's going to be fitted to the Sputnik for the launches this summer, because this rocket is much heavier than the rockets that have been launched earlier on, so they need to have more buoyancy for the launch pad, and that's why the third hull has been constructed. And they have I'm just gonna tweet it here. They have been threatening to roll this hull out during most of the day. Thank goodness that hasn't happened yet, because I think it will be extremely noisy once they start doing that.
Yeah, they wanted us to move this outside broadcast unit, as we would call it. It's not only recreational; it's also a broadcast unit.
It certainly is.
And well, we keep talking while we know they must now. They left the upper deck. But yeah, it is quite fantastic that, and it shows something about the strength of this voluntary organization, that people do what they have to do, and the guys that are charged with preparing the launch pad, they just keep on working. They don't care if there's a party outside.
Precisely.
So that is really nice, and that shows some of the strength of kind of strange visionary planning system that you, even though you always look very far ahead, and that's what what is being done here. Now we have the engine. I haven't. What is the name of the engine? The name of the rocket is HEAT-2X, and the name of the engine is
TM65LE, and I honestly don't know what either TM or LE stands for.
Okay. Anyway, yeah. But the engine is there, and the vanes, the fins, and the vanes in the exhaust are in place. The rocket is painted with sort of its black and white checkered livery, so that you can study later on. So you can study how it rotates while it's going up, and you can get a clearer picture with the telescopic lenses that follow it from the ground, in addition to the tracking radars the tracking radars and the locator beacons. But now I think that we must be coming up towards we're coming up towards a burn.
When we look at the images from the pad right now, I actually don't see any people.
There's not a soul left there anymore.
Nobody on the pad, nobody around the pad. The radio is silent, so whoever's talking is doing it without using the radios. But we know that all the liquid oxygen has been loaded into the oxygen tank. We know that the fuel, the alcohol, has been loaded. It was done earlier on. And we can see that there are no more any people on or around the pad. So we're actually just
So what
waiting.
do we know about the checklist that they must be going through right now? I mean, we know that they're coming down to pressurizing the oxygen. And after that, it will be the countdown. Yes, within pressurizing the oxygen.
I would think so.
Yeah, and then that's a countdown. Right now, they'll be running through the checklists of that basically will be first of all checking all of the sensors. That is most important. I would guess. I don't know.
We also know that they have a lot of high-speed cameras.
Yeah.
On the pad to film the exhaust and the jet vanes, how they perform inside the exhaust. And as far as I know, a lot of those cameras cannot be remotely operated. They have to be started manually, and they can only record for quite a short time, because they do it at such high frame rate. If you start a camera recording with 1,000 frames per second.
Oh yeah,
you don't have
gigabyte in 5 minutes.
Precisely, you don't have hours after you start such a camera.
And still rising, we are heading for a
so the camera will the countdown will probably
which we will have our
need to start sometime soon. Yeah,
camera.
now we have a great shot of the.
Og Thomas, jeg skal lige høre, når vi når til det der 18 bars hold, vil du tage den ene tank op til 18, og så den anden tank op til 18, og så sende fotograf over, og så tage den op til flight pressure, eller hvad? Skifter. Det var tanken, ja. Det er modtaget. Okay, we're at 6.4 bars on the fuel and still rising. Thomas, vi har stadigvæk en tvivl om en sensor i oxidizer-tanken. Vi ville faktisk være meget glade, hvis I skiftede over og bare gav os en bar i oxidizer-tanken, fordi vi har simpelthen et problem med, at den viser stadigvæk 0,2 bar, efter vi har stået i LOX closure i ret lang tid. Så enten er der hul i tanken, eller også optager den ikke for varme for omgivelserne, og ingen af de dele kan være sande. Så det ville være dejligt at se sensoren vise noget andet end 0,2 skifter.
Ja tak, vi skifter over til en heliumflaske.
Eller hvis I bare kan køre den op på en bar, så vi lige kan se, at der faktisk sker noget der. Hvis det er, I ikke kan det, så er det jeres manometer, der viser sandheden. I den ende af slangen, så er det den, I kører med. Skifter.
Ja, det er forstået.
Og I er på 8 bar i fueltanken. We'll pass the 8 bar threshold on the fuel tank, and we will just have a little bit of pressure applied to the oxidizer tank to verify that the instrumentation is go. The pressurization of the flight tanks of the rocket are the final procedure before the firing of the engine. So we are in the final procedure. I'm expecting full tanks, full pressurized tanks, sometime around 16:15, which would make the firing hitting before 16:30.
Tryksættes LOX-tank nu.
Modtaget i tryksætter LOX-tank, vi viser stadigvæk 0,2 her.
Status på LOX.
Thomas, hvis I lukker på flaskeventilen på heliumtilførselen til ildtanken, så vil du se jeres manometers opfattelse af trykket i højtrykssiden af ventilen, og det vil sige trykket i ildtanken. Så hvis I lukker på flaskeventilen, vi ser nemlig ikke nogen stigning herover, skifter. Ikke 0,2 bar på oxidizer-tanken.
Okay, vores instrument viser 12 bar.
Kunne du gentage den, skifter?
Vores instrument viser 12 bar.
Så det er jeres instrument, der har ret. Hvis I har 12 bar på oxidizer-tanken, så har vi 12 bar på oxidizer-tanken. Så det går meget hurtigere med den er, at det er helium, som har en meget lavere fluidmodstand i rørsystemet. This concludes, we have one sensor down. Our readout of the oxidizer tank pressure is not consistent with analog instrumentation showing 12 bars. This means it's the analog instrumentation that is the reference.
Kan vi få en trykmåling på fuel?
Hvis jeg lige må få den igen, Thomas. Kom ind, skifter.
Trykmåling på fuel, tak.
10,4 på fuel.
Ja, vi er nødt til at skifte nitrogentank. Den første er tom.
Modtager iskifter nitrogentank. Jeg har en forespørgsel fra Per. Han vil lige tjekke en mulig lækage i helium op på den prop, han satte i. Så med jeres tilladelse, så vil vi have Per op i tårnet og tjekke op fra adgangsbro 2, at hans prop er tæt. Der skulle ikke være noget problem i det, hvis der kun er 12 bar på den skifter.
Ja tak.
Okay, Per, du går bare videre. Har du en radio med op, skifter?
Ja, jeg er på en radio, og jeg er på vej.
Så er vi der nu. Ja, det ved jeg se engang her.
We are back again, and we now have actually radio communication audio in our ears
Yeah.
right now, so that we can talk.
We continue to pressing both propellant tanks. We are now verifying tightness of the helium storage on the oxidizer tank. All systems are still go for the test. Pressure is rising in the nitrogen system on the fuel tank, passing 10.3 bars.
Okay.
Right now changing the cylinder so that we put a fresh nitrogen cylinder on.
Jeg fortsætter tryksætningen på fuelsiden.
Yes, tak skal du have. Per, når du kommer ned, så må du godt åbne oxygen chill. Den skal vi tage i gang nu, skifter.
Ja, det må jeg.
Den kender der heller ikke noget nu. Hvis det skulle være åben nu, ikke?
Ja.
Men nu tror jeg Peter.
Vi har en læk heroppe, Peter.
Ja, men severity level. Hvor galt er det, skifter?
Det er sgu også et spørgsmål.
Men okay, godt. Videre i teksten. Du må godt lige prøve, om du kan efterspænde den der, og ellers så kom bare ned, og så få åbnet for chill nu.
Efterspænde, lige deroppe.
Ja, men giv den lige et niv, og så akustisk verificere, hvor meget det er. Hvis det er en lille smule, så er det en lille smule en kæmpe tank.
Det må jeg tage.
Ja, det er den sidste spænding, der nu koger i kontrolrummet dernede.
Tryksætningsstation, hvad er jeres visning på ildtanken nu, skifter?
Den siger 11 bar.
Det er modtaget. Det giver mig en severity-måling på den der lækage, vi har. Det er inden for, hvad vi kan klare uden problemer.
Peter Madsen and somebody we don't know who is
Serving a small leak on the helium system on the oxidizer tanks, but it's within limits, so we're able to continue down to the firing.
Det er altså tryksætningen af den flyd.
Du kan give mig noget chill, så vil jeg være rigtig glad. Vi skal have kontrolleret temperaturen på den der tank, når vi begynder at putte rigtig meget helium i den, skifter.
Nu begynder det at gå stærkt.
Ja, det må jeg tage, men kan du måske på Rune over, mens jeg spænder?
Jeg spørger Rune, om man vil gøre det.
Skal jeg gøre?
Du skal gå over, og så skal du åbne for chill. Det vil sige, du skal bare åbne over på en af lokstankene. Og så skal du bare køre noget gas ind i den.
Jeg er på vej over at åbne for en tank.
We are now turning on the oxygen cooling system in preparation for the test. Audience will be able to see a jet of ultra-cold oxygen coming out of the side of the rocket. This is nominal. It's part of the chilling system.
Jeg bliver Rune her. Ja, Rune. Åbner nu. Åbner.
komme her til containeren. Jeg kommer over.
So as I can gather right now, there's a leak in the oxygen system, but as far as I can understand, it is not considered critical. So it will be possible to go through with the test in spite of the leak.
Yeah, small leak and actually proceeding.
Her Peter, jeg har begrænset udløbet til cirka det halve.
Ja, de spænder ventiler, de spænder i sidste øjeblik. Her går de og strammer op på det.
It sounds like they've been able to reduce the leakage to half of what it was before. That is, of course, an improvement.
But even the outset, it was nominal. It was within limits. Well, that is exciting. Yeah, as you can see in the background, there's a big power plant, one of the power plants of Copenhagen. One of these chimneys, one of these blocks, HEAT-2X will for 90 seconds anyway at the start produce as much as one of these blocks in the power stations of Copenhagen. This tiny little rocket, which is a huge rocket for Copenhagen Suborbitals.
We now see people running around the test stand, and I was going to say these are probably technicians, but now I see one of them is carrying a large microphone, so it looks like a camera crew. Somewhat surprising to see camera people running around a pressurized rocket, but I suppose someone has taken a decision.
Maybe we can borrow money from them.
Yeah.
Maybe. And remember, we don't know anything that you don't know with regard to how far we are from the engine firing. We're listening in on the radio communication just as you are. Last thing we heard was that there was a leak in the oxygen system, but it's been reduced and it's not going to be critical for this test. So
it will be soon.
It will probably be soon.
It will be soon, yes.
Godt, kan jeg få en bekræftelse på, at tændingssystemet er desarmeret?
Ja, altså jeg har ikke sat boksen til endnu, men her på min skærm ser det. ikke ud til at være det. Du har ignition load, og alt andet er off.
Mange tak.
Well, it looks as if somebody climbing the tower, and they climb there up there beside the rocket. They have disarmed the ignition system.
And that is Peter Scott, who is data and radio communication guy in Copenhagen Suborbitals. There's a 1-hour video on YouTube where he explains all the different aspects of radio communication in Copenhagen Suborbitals, which is very interesting.
It looks like a camera he's moving around.
He's definitely mounting a camera. Can we switch to the view of the bottom of the rocket? We're trying to get a picture for you to see where you can see the bottom of the rocket.
Peter? Vi skal lige skifte det billede. Skåret op og ind på noget, så vi kan lige have bukken og
Det der kamerastart, det skal gå så hurtigt som muligt.
Before.
Men husk for guds skyld aksonometerboksen.
Yeah, the camera on the lower right of this frame has just been moved around. Maybe it was Peter Scott. The
Det er vagtchef. Har vi et tidsestimat med hensyn til publikumsfotograf?
Ja, det der kvarter, det har vi lige baseret.
Okay, så må publikum godt gå op og sætte gangen start deres kamera.
Okay, there's people can go and start their cameras now. Yeah.
Helt jæv.
Kom en jæv.
Bagsiden af bakken ser fri ud fra mit udsyn.
Ja, vel. Vi har haft sweepet lidt længere ned. Du melder bare, hvis du ser noget.
That was one of the range safety officers checking that the hill behind the exhaust plume is cleared and free of people, and we now see people moving away from the pad. We still have one person working. We have 2 persons working right beside the pad right now.
Safety shot er fjernet. Det er vagtchefen. Jeg har sendt publikumsfotografer op og tænde deres kamera. De har ordre til at gå ned igen med det samme. De er væk igen om 3-4 minutter.
Okay, these are last preparations, and well, we are 13 minutes past 4. That is 16:13 Danish time. Yeah, 14:13 UTC, and the burn must come. The firing must come soon. Isn't that Peter approaching? That is Peter Madsen approaching. Checking something with the liquid oxygen tanks.
Trykmåling på, hvad vi nu kan få trykmålinger på. Ja, 15,8 på fuel. Og LOX, den er 0,2, men det står vi så ikke på.
So it sounds like there's a problem with the LOX pressure sensor. we just heard some pressure readings. The alcohol is pressurized now to, was it 15.8
15, yeah.
bars, and the liquid oxygen pressure reads out at 0.2 bars, but they don't trust that measurement because of the bad sensor. And that of course begs the question, how will they determine the pressure inside the liquid oxygen tank?
Fuel tank. Fuel er 16,5. Tak.
Well, fuel is rising. So fuel is close to the nominal value that for the fuel that was 20.
18 or 22.
Yeah.
I think they were going to be pressurized at two different pressures. One was 18, one was 22. I don't remember which was which.
Okay.
Well, we probably still have some time.
17,4 på fuel.
17.4 bars on the fuel. And we're hopefully going to see the ignition of the HEAT-2X rocket with the TM65LE engine below it. The rocket will not leave the pad. At least that's not the plan.
It's a so-called static test, yes.
Static test.
It's actually chained to the pad.
It is.
Four big.
All plan can be changed.
Yeah. All chains can be broken. That's right.
We had a question on Twitter earlier on. How do they make sure that the rocket doesn't leave the pad? No, I believe actually the question was.
Har du observeret noget siden vi talte sammen sidst?
Ja, jeg tjekker lige igen.
The range safety officer checking the area once again. Another sign that we are approaching ignition. I know it says on your screens expected burn in 15 minutes, and it has been that way for quite some time. It just changed. Okay. 18.3 bars in the fuel tank. So that must mean that the fuel tank is going to be pressurized to 22 and the oxygen to 18.
Yes, we know once we reach the nominal pressures, it will be 20 seconds, 19 seconds to firing. So it is going to happen very soon.
Peter, could we have feed 1 up there?
Trykket i fuel. 19.
19 in the fuel tank. We're getting closer. We're just changing the view now to a camera where you can actually see the liquid oxygen boiling off outside the rocket. Alexandru Seta his Twitter username is CSETE. He just tweeted a picture of the HEAT-2X rocket taken up in the pad, looking down alongside the rocket, where you can actually see a 2 millimeter thick layer of ice covering the oxygen tank.
Kan vi få en eller anden i bunkeren til at give mig nogle data?
19,6.
Nu vil jeg gerne have data for hver 10. del, bare den stiger.
19,7.
19.7 bars.
And rising. That's the pressure in the pressure is rising.
Pressure is rising in the fuel tank. Fast. 20 bars.
20,4. 20,5. 20,7. Over 21,2.
21.2 bars.
In the fuel tank.
So the fuel tank will be pressurized shortly.
Yeah. Finish pressurizing and then we... Yeah, life goes on in Copenhagen. Outside we have some kind of a workout session going on, the neighbors.
We also have a lot of speak out there.
Yeah, and they also have countdowns, that was what I was saying. But they'll get one they never will forget in just a minute.
Precisely. Yeah. It's somewhat confusing to suddenly hear a loudspeaker.
22.2 for the fuel tank, so that's it. The fuel tank is pressurized.
That's interesting. We still have oxygen boiling off. 22.6. How far will they go?
Still rising, yeah.
I thought they were going to stop at 22, but apparently they're continuing. And again, as far as I've understood, the pressurizing of the alcohol is being done with nitrogen. 23.1.
We have a safe release valve open. That's okay. Or it might be the burst disc.
And in this view,
we've had a burst disc opening. The system is stable. It will go down in pressure. We will not be able to fire the engine.
Wow. Look at it.
The root cause of this situation is the failure of the oxygen transmitter that should tell us the pressure. And now we've passed into the region where it's too high, so the burst disc blows. That means we have no test today.
So apparently the test is off. A safety valve has blown on the liquid oxygen tank and is now venting all the oxygen to the outside because the pressure
we see it now.
Goes too high because of the fail
sensor. Yeah. Too bad, but the engine the engine is safe and can be it can be. Nothing was really ruined.
But so what a pity.
Yeah, what a pity. Nice day.
Yeah.
Yeah. Yeah. Yeah. Yeah, what a pity. It was almost there. Almost.
So close and yet so far.
Yeah.
But of course,
there's unfortunately no way that we can reverse the opening of the burst disc. The burst disc is a safety measure, and it means that once it opens, it's a one-way ticket to no test. And the only thing that we can do now is to replace the faulty sensor, empty out propellant, reload propellant another day, and do another test.
That's it. That's it. Yeah. Yeah.
That's it. Well, that's
but
rocket science.
It's been a nice day. Yeah, and sure, and we still have the rocket, like Peter said. Just we'll have to empty it. The oxygen can't be reused, but I suppose that the alcohol can. You can still use that.
Probably.
You can. Jeg tror godt, jeg tror nok, jeg gerne vil stoppe her, fordi jeg har gæster. Jeg har Yeah. Well, there sure will be another test. It was a simple little sensor, like Peter said. It was a safety measure. It was a one-way street. Once that safety valve had gone, there was no way to stop it. It would just vent all of the oxygen into the air, and that's what happened. And but there's only one answer to that: is refuel the rocket and make another test another day. That's how it goes.
That's how it goes.
It was a beautiful day. It would have been great, and
It certainly was.
Yeah. I personally, I'm gonna miss the noise. Thank you to everybody out there for listening. We're signing off. Jan Haugaard and
Sten Eiler Jørgensen.
Yeah.
Thank you for joining us for this live stream. And for us, this was a great dress rehearsal. This might be even better the next time, and that's the way it always is. When you have to call off something, you get the chance to do it again.
Yeah, you can put it another way. We love mistakes because that's the only way you learn.
It's the only way to learn.
Yeah,
that's right.
So, thank you very much.
Thank you very much, and bye bye.
Bye bye.
Morten Jev. Kom ind, Jev. Kan man komme ned ad bakken? Safe approach. Ja, men du kommer bare stille og roligt ned, og så hvis du kan gå sådan nogenlunde bag de der over. Altså, vi har mistet alt tryk på lokstanken, og vi har stoppet tryksætningen af, fuel, så det burde være rimelig sikkert at komme ned stille og roligt. Det er modtaget.
Publikum, vi har godt nok ikke nogen raketopføring i dag, men vi kan lave en rundvisning over i HAP 2, hvis I har lyst til det. Så de flinke vagter vil vise dem, der har lyst til at se HAP 2, det er over her lige om et øjeblik. I skal bare følge med. Gentage vores invitation til en rundvisning i HAP 2 her umiddelbart efter denne test.
Rune, vil du have taget trykket af nu fra fueltanken? Vil du have taget trykket af fueltanken nu? Ja, det vil vi meget. Lad mig lige summe over den 2 sekunder. Ja, vi tager trykket af nu. Det er Peters kommando. I hvert fald dukker vi os lige indtil I siger, at den er nede på 0, ikke? Hold lige. Fortro skal i sikkerhed igen. Ja, vi tager trykket af fuel nu. Den er på 22,1. Ja, den kører langsomt ned af 21,3.
16,4. Ja, spiller du, der trykker så lavt, at jeg kan lukke publikum op og hente deres kamera?
Jeg er 13,4 bar nu. Only, did you close the valves on the helium tanks?
All tanks are closed from my side.
Okay, thank you. So we have a surplus of helium in the tanks right now?
Tank that is unused and another one with, I don't know how many bars on, half full, something like that.
Thank you.
Vagtchef er ved at trykke ned på nu.
Data kan I svare på tryk? 7,8.
Hvor langt skal det ned, før jeg kan lukke publikum op og hente deres kamera?
Jeg tror godt, de kan komme derop nu.
Vel.
Super i fjorden.
Thomas Pedersen, det er Lili.
Ja, Thomas.
De har lukket ned for livestream, så du behøver ikke komme.
Mange tak, Lili. God skat.
Selv tak.
light flight photo. Flight til i morgen. Til morgen.
Hvor vi kan lave publikumstur nede ved prøvestanden.
Thomas P. til Morten, kom. Thomas, vi snakker lidt om vi ikke skal tabe spritten af i dag, når vi nu alligevel har det gode vejr.
Jo, men det er min holdning er, at spritten skal af, men vi skal også lige høre Peter, hvad han siger.
Okay, hvis du lige gider at planlægge vores depressurization her, og hvad vi lige gør for at lukke ned, så vil det være fedt.
Ja, jeg kommer op.
2,5.
Elof, det er Lille.
Men Lille.
Der er ikke åben, I har haft 2 for jer view.
Lige 2 sekunder. Gentag lige en gang. Jeg skal lige udenfor.
Der er ikke åben, I har haft 2. Nu er der. Det er forlært, at jeg har sagt noget forkert så. Vi tager
Thomas til Bulskov.
Ja, kom ind.
Bulskov, vi skal have alkohol tanken hen foran, så vi kan dræne motoren.
Det gættede jeg på. Så jeg, kører dem hen foran. Carsten Olsen.
Ja.
Gider du at gå op og lukke, high speederen ned? Vi har 0 tryk nu, og så tage dem med ned.
Det gør jeg, når flight siger go.
Ja, men flight har sagt go.
Husk, vi har en oprydningsopgave i HAP 1.
Okay.
Den må I gerne hjælpe med, når I er færdige med, hvad der er presserende.
Alex til Morten, kan du høre mig?
Godt, det er jo.
Ja, det er godt.
Din wifi-boks, er den vandtæt? Står siden af antennen.
Kan du ikke lige flytte Carsten ting over på den der beholder? For den er...
Jo, det tror jeg ikke.
Eventuelt bare lægge dem over på vandtanken, den skal jeg ikke bruge lige nu. Jeg har taget slangen. Der lå en gul slange. Herpå. Tabt et eller andet. Den skal bare blive der. Det er pumpen, vi skal bruge. Jeg også lige holde til at flytte stolen, inden jeg knuser den.
Kylling.
Ilof til Morten.
Mejling til Jæv. Øjeblik. Har du stillet alle kameraerne?
Kameraerne står på stenene ved siden af blå container.
Tak skal du have. Morgen, det er Mejling.
Mejling, du så godt rødt, de røde kasser stod på den bagerste af ståldragen, ikke?
Jeg går faktisk og leder efter dem nu. Jev han sagde, at det hele det stod over ved containeren.
Han har taget kameraerne over. Jeg ved ikke, om kasserne er kommet med. Jeg går lige over og kigger herfra.
Nej, jeg ikke. Okay, hvor står de henne?
Over på den bagerste af ståldragen. Jeg satte dem deroppe, hvor de var lidt i skygge.
Godt tænkt.
Elof, morgen. Elof til morgen. Der kan høre over den her kanal, så må de meget gerne komme ned og hjælpe med at rulle noget vandslange og nogle ting sammen. Det er ikke så meget, der mangler hernede. En halv times arbejde cirka.
Det var Elof. Er der nogen med radio, der har visuel på Jonas? Der har visuel på Jonas.
Står ved teststand, jeg kan ikke se ham.
Er der nogen i HAP, der kan høre mig?
Ja.
Kan du scoute lidt efter Jonas op i det område?
Undskyld, jeg misforstod. Jeg har my bad. Hvem var det, der efterlyste Jonas?
Det var flight.
Har Jonas nede ved bunkeren nu?
Okay. Kan du spørge Jonas, om han har lyst til at lave en temperaturmåling mere op i motorrummet nu, hvor det er koldt?
Det har ingen betydning, siger Jonas.
Okay.
Pat, har vi mulighed for at lukke publikum ned til prøvestanden? Er der nogen, der frygtelig gerne vil have en tur?
Jamen, de må godt komme herned.
Vel.
Carsten til Thomas.
Ja, Thomas.
Så det kamera ned, der sidder deroppe.
Det skal jeg gøre.